retrievals on HD209 by Paolo. I give you the 2-minute hot wave.
Okay, thank you. Good morning, my name is Paolo Giacobbe, and I work as a researcher at the Astrophysical Observatory of Turin. Okay, my original title was Exoplanet Retrieval combining high and low resolution. I had in mind something general on the big catalog of JANO observation. But after a while, I decided to switch to another title and focusing on the trouble story of HD 29548b. So let's go. Please notice the Greek prologos, that is the starting of a tragedy. So this was in 21 when we published with the detection with JANO of 5 carbon and nitrogen species that we detect in cross-correlation. After a few months, JWST flight, and here we are in 2023, with the first transmission spectra from JWST. And okay, if you are looking for a definition of a cold shower, here we are. Unfortunately, no evidence of many secondary species, but okay, the cold shower wake up, so let's go. The first question is, how do we compare these two measurements? Okay, the most simple idea could be to start from the template that we use for the cross-correlation, scaling in some way these templates, and try to see if the line of this scaled model cross the dots of the JWST spectra. Unfortunately, this doesn't work, because the cross-correlation technique is insensitive to a scaling factor, is a quite simple answer. Maybe a good question here is, are the cross-correlation detection informative about the atmosphere of the planet? I will try to answer at the end of the talk. By the way, in the work of 2021, we did some work that could be useful to compare our detection with the JWST measurements. We switch from the cross-correlation, okay, I try to point. We switch from the cross-correlation, use in a likelihood, in a Bayesian framework, we compute a self-consistent grid of radiative and chemical equilibrium models, and we perform basically a grid retrieving. So we test this grid on our data. And this is what we obtain. And does it work? Unfortunately, not. Again, it is becoming annoying. Okay, the dot here is the JWST measurement. So apparently, also with a proper comparison, we are not in agreement with JWST, but never give up. Basically, we switch in a fully Bayesian framework, in a retrieval framework. Many people talk about this during the conferences. Okay, there are many different details, and the evil is in the details, but no time to explore it now. Basically, we have two approaches. A 3 parameters approach, that means that everything is free to, the algorithm could explore everything about in the parameter space, and a thermochemical equilibrium approach. That means that all the chemistry of the planet atmospheres is related basically to 2 parameters. There are the carbon to oxygen ratio and the metallicity. This thermochemical equilibrium is computed by the ChemCam code. We use 2 radiatory transfers code that are Pirate Bay and Petitra Trans. Here there are the line lists that we are using, so lesson learned from the previous talk, and we move on. This is the results of a retrieval in chemical equilibrium with our full data set. Okay, there are many things to comment here, but I want to focus on the metallicity plot. We basically see a double peak. That means two things. The first one is that the new setup, we are basically in agreement, still in agreement with the result that we have in 2021. And the second thing is that in 2021 we miss the peak at higher metallicity. And the things are going better because if you put the JWST here, we are only 2 sigma away from JWST. Before to go deep inside this retrieval at high resolution, I want to do a small dive into the low resolution data. And the first thing that makes me curious is this offset between JWST measurement and the Hubble Space Telescope measurement. Okay, this is the projected model from JWST in the HST range. Where arise this offset, that make basically the two measurements incompatible? There are at least 2 reasons that I have a few seconds to explore. The first reason is the limb darkening. As you can see, the limb darkening is a fundamental parameterization of the light curve. And as you can see in the work of PRSA 2016, for specific mu angle impact parameter, the difference between the standard quadratic limb darkening and a physical motivated limb darkening could be up to 10%. And this could lead to, to big systematic error at the end of your computation. The people always said that the low resolution is model independent. That is true from the side of the exoplanet, but is less true for the side of the star. The second effect is the impact of the stellar activity. There were some talk about it. Normally, the impact of stellar activity is extremely high in the optical part of the spectrum, but also in the near infrared, in the infrared, could lead to a systematic offset of few hundred parts per million. That is close to what we see here. It's not my intention today to say that which one of these 2 measurements are right, basically, but it's interesting to explore what is the effect of this offset. Basically, these are the 2 retrievals on the 2 datasets. Many things to comment, but the main one that I want to comment is, again, the metallicity. As you can see, this offset could lead to a difference in the metallicity of many orders of magnitude, basically shifting from a subsolar metallicity to a supersolar metallicity. So a systematic effect on the final transmission spectrum could lead a very different scenarios in the chemistry of the planet. Now we come back to the high resolution retrieval, and to explore my initial results, I divide our 4 transits of HD 209 in 2 seasons, and what is clearly visible here is that we have 2 different dynamical solutions for the 2 seasons. But, okay, basically I am climbing a variability. The problem is that I don't know which kind of variability is. Could be astrophysical, but until now I was not able to disentangle this variability from, for example, instrumental stability, atmospheric problem with the telluric and so on. This could lead to this simple law. 1 measurement, 1 paper, 2 measurement, 0 paper. And I am in this right situation. I did the same stuff with a free chemistry approach. I basically see the same pattern in the dynamical solution. But if I zoom in the volume mixing ratio corner plot, I see 2 interesting things. The first one is that the equilibrium chemistry that here is shown as the gray lines is driven by the volume mixing ratio of the water. The second interesting thing is that some secondary species start to grow up with 2 sigma peak. I know very well that this kind of peak with a long tail are not constrained, not significant. So I prefer a more Bayesian approach. That means that I test the possibility to consider these species inside our model with a Bayesian test. I use the archaic, this is the final values for this particular case, that led me to a significance that is between positive and strong. So to fit my data set at high resolution with a free chemistry one-dimensional model, I need, looks like that I need some secondary species. Unfortunately, it's not a full confirmation of what we see in 2021, because in a retrieval framework, there are at least 2 explanations for these secondary species. The first one is that you need to explain the lines. That is what we always said about the high resolution. But also at high resolution, we are in some way sensitive to the continuum. As you can see between these 2 different models, the presence of secondary species dump basically the line of the water. So maybe you need a secondary species only to dump the line of the water, but it doesn't mean that you really need this species. You really see the species in the atmosphere of the planet. Okay, I put this one basically because I put in the title the combination with height and low resolution. This one basically tell us one thing, that JANO, at least one season of JANO is in agreement with JWST, at least in chemical equilibrium, as you can see here. But we are not still able to solve the puzzle of the secondary species. Maybe it's, our framework is not enough to explore something that needs this equilibrium, something very far to a one-dimensional approach with volume mixing ratio profiles that are really different. So look at the C2H2 here in this equilibrium approach, something that is so far, really far to be constant. So, okay, these are my conclusion. I obviously no time to comment everyone, but I want to say that I still believe in my detection of 2021, and in particular, I think that are still useful in the JWST era, because maybe we will find that the secondary species are accessible mainly with high resolution for its nature or for the part of the atmosphere that we explore. This is my official conclusion, but now there is the 2 HoRSEs final slide. I'm looking for something with a horse and a French bulldog. So I asked to ChatGPT for a sketch with these 2 animals, and I obtained this one. I appreciate the irony. This is basically my one-dimension model of the reality. So, but I come here at this conference and I see many spectacular tools. So I ask to another tools, and I obtain this one, which is stable. But in any case, this is still far from the reality. So, okay, thank you for the attention.
Well, hello everybody. So I'm Florian Debras from Toulouse. I thank the organizer for giving the opportunity to talk a bit about degeneracy and bias in high-resolution retrievals. And I'm going to do it in 3 parts. So I'm going to put a bit of context. And then I'm going to just mention radius, temperature, and composition, which was the first we tried. And finally, I'll finish with what we can do with ANDIS and speak a bit about dynamics. So because there are many sources of biases and retrievals in high-resolution spectroscopy, you have to make some choices. And this is going to be a cloud-free talk. So I made this choice, and I hope this will make it a clear talk, but that's not very clear. OK, so why did we want to study this? Is because in the low-resolution spectroscopy community, they have a lot of understanding of their biases, the degeneracies. In our community, we have much fewer work on simulated data. And so we tried that. We wanted to assess the bias and the degeneracy. And what we did is that during the commissioning of Spiru, they observed the star JG15A, which has no transiting planet, for a whole sequence of a few hours. So it was a perfect test case to put a planet on it with no other planet on this observing sequence. And so we put an observational equivalent of HG189. And we present results about this on these papers. And I just wanted to mention that we use spectratons and multinest, so that might be of interest. All right, so Tia already mentioned it yesterday. This happened in the framework of the Atmospheric Consortium. So that's a gathering of people basically to optimize the chances of getting telescope time. And we have already 4 papers published and more coming, but Tia mentioned that. I just wanted to say 2 things about it. So we have this open source pipeline. You can go for it, and it does what everybody else does, basically. So you have a physically driven data reduction, followed by the data-driven data reduction. Today I'm just going to speak about the PCA method, but you have the autoencoder method in the paper. And then we generate spectra with spectratons, and we do a statistical analysis like everybody else. But I just wanted to emphasize how we do our PCA, because Jane mentioned it yesterday or 2 days ago, I don't remember. But basically what we do is that we do something which is very driven by the data, which is not driven by optimizing the correlation. So we estimate what is the dispersion that you should have if you have a map of white noise, and we take off every PCA that has an eigenvalue that is above that white noise dispersion, so taken from the data. And so, for example, for our data, you have here the eigenvalue of each PCA component as a function of the number of the component for 3 Spiru orders, so going from the reddest order to the bluest order. And you see that the shape changes. And so when you have a big symbol, it's a component that we take off, and the small symbol is a component that we keep. And so you directly see that in the reddest part of Spiru, we take off 6 components, whereas you just take off 2 in the bluest part. And that is driven, again, by the data, order by order. All right, so the first conclusion that we had, which I think it's important to mention, is that we have a bias in our pipeline. That was a bit surprising, but I'm going to explain it. So this is a posterior for the water content and equilibrium temperature for a vertically uniform model that we put in the data. And we see that in the reference case, it's OK. We are not really centered, but there is some noise. It's a simulated spectrum, but on real data, so that's all right. But when we go to a planet that has a large rotation rate or a much slower KP, a much lower exploration of the speed during its orbit, we see that we are biased. So we still are OK at 2 sigma, but we are completely biased towards lower water content and higher temperature. And this is something that is always the case in different models. And that we are trying to solve in an efficient manner, because that's not very easy to be efficient for this. But what I wanted to mention here is that, so in our paper, we are not in this case of reduced KP, so we are fine. But I don't think we are the only one with such biases, but we are the only one that looked for them. So I would suspect that there are some other biases in different pipelines around the room. All right, so the first thing we tried regarding degeneracies, it's a very simple one, is what happens when you have a planet where you're not sure about the mass or the radius. So for example, for young planets, we will have uncertainties in the mass because of the activity of the star. And so, of course, if you impose a wrong mass or wrong radius, well, you have a bias because you will change your atmospheric scale height. But what you expect, and so this was kind of a sanity check, is that your observability should scale as roughly your atmospheric scale height times your planetary radius divided by your stellar radius squared. And so this is proportional to planetary radius divided by gravity. And this is exactly what we find, actually, is that if we don't retrieve gravity or radius, we have biases. But if we retrieve just one of them, we get a good ratio. So it increases the degeneracies with temperature and composition because you have another parameter. But we always retrieve the good ratio that was inputted in the model, and we remove the biases that was created from a wrong mass or a wrong radius. So that's kind of equivalent to a scaling factor, but it's going to be important for planets where we have big uncertainties on the mass or radius in the future. So that was kind of sanity check that everything works as we expect. And then we moved on to temperature. And so what we did is that we created vertically uniform model in composition. Sorry. So vertically uniform model in composition, but not in temperature. And so you have here the pressure temperature profile, and in black, it's the one that we put in the model that comes from a GCM simulation of HD189. And then in the other colors, you have different temperatures that are retrieved with different approximation assumption on the model. So this is for a water volume mixing ratio of -3, and if you go to -5, you have something that is very different. So that's complicated to understand right now, but if you just zoom in on the region where the optical depth of water, which is 1, what you see is that your model are trying to optimize the temperature where the optical depth of water is equal to 1. That's to be expected because we know that transmission spectroscopy, so here it's transmission of course, as I mentioned, is much worse than emission spectroscopy at retrieving the temperature, and at our low signal-to-noise ratio, we really have a retrieval only around the optical depth of 1, and the rest is just dependent on your choice of priors and your choice of model. We are completely insensitive to the rest above it or underneath it, so we have to be very careful about that. And if you have multi-species, you might find some temperature at different levels, but you have to be very aware that the transition between all of this will just be dependent on your model. All right, and finally, and that's very interesting to go just after Paolo, because we will have some similar conclusion, is we looked at models with different molecules. So in here there are 3 molecules, water, CH4, and NH3. And what you see is that your posterior distribution are clearly not beautiful round Gaussian, if you wish. You have a clear degeneracy between the species, and the first thing you think it might be a molecular weight effect that changes the size of the atmospheric height, but not at all. It's not a molecular weight effect. And what it is, actually, it's exactly what Paolo mentioned, and you can see it here. You have here 3 models going from the green to the to the blue. They all have the same amount of water, but we increase the amount of CH4 and NH3 from green to blue. And so what you see is that you create some new lines in the blue, that's expected, but you also shift the continuum slightly higher, while you don't change the maximum radius because the water content has not changed for example, for the strongest line. So what that means is that the relative amplitude of your line has decreased because you have added other species. And so if you want to keep a relative amplitude that is constant, which is what we do in high-resolution spectroscopy, we are sensitive to relative amplitude, then you need to increase the water content to mimic this. And so because we are not sensitive at all to the absolute value of your radius or whatsoever, you lose the information of what is the absolute content, and you create this spurious degeneracy. And you need the combination either with low-resolution spectroscopy or maybe with other ranges of wavelengths to lift this degeneracy and understand what's happening here. But what that also means is that sometimes you can have minor species that are not detectable, but that still have their lines won't be detectable, but they still have an effect on the continuum. And so if you don't include them on the retrieval, you will have an error on the value that you retrieved for the species that you detect. So we have to be very careful about that. It's not because you don't detect a species that it doesn't have an effect on the retrieved abundance of the other species, at least in our low signal-to-noise ratio case in here. All right, so that was the first 3 stuff that we tried for this paper. So there are many other sources of degeneracy, and we are trying to understand some others. But well, as I said, we have to make some choices. And I just wanted to mention, to finish, what we are doing with to understand what's happening in the dynamics with ANDIS. And so I have taken this plot from a talk of Matteo Broggi, and you have basically the expected signal-to-noise per unit for normalized signal-to-noise by instrument for different instruments. So going from JANO, the first version of JANO, to Spirou, and iGreens and the Gemini is not here. And what Matteo said to explain why Spirou was above CRS Plus, for example, is that you can compensate a small aperture with an increased range or efficiency. And so when you think about that, the problem of CRS Plus is it has a very small wavelength range. The problem of Spirou and Carmenes is have a small mirror, and the problem of iGreens, which is not here, but anyway, it has a lower resolution. And so what could we do is create an instrument that resolves all these problems, and this is exactly what ANDES does. It has a large mirror, a large wavelength range, and a very high resolution. And so I like to say that ANDES is a kind of steroid-boosted version of current spectrographs. And to be in the host team, basically, in a few years, we'll go from this nice Peru horse to the Andes who's coming. So that's our future, and we have to be ready for this. And what we've done for the Phase B science team is that we simulated data from a paper by Haley Biltz. So this is Haley Biltz, sorry. That's WASP-121b simulation. So we have a 3D spectrum, and I created a simple simulator to simulate some Andes data if you want to play with. It's very simple, but I put it open source. And what you see is that, well, you have some temperature effect, but you have a planet that rotates at basically 6 kilometers per second at the equator, and you have a super rotating winds that is basically at 5-6 kilometers per second again at the equator. And what we've done is we try to retrieve that with either Andes simulated data or Spiru simulated data with 1D models, so really simple models, but analytically broadened with the kernel of rotation. And what we obtain basically is that on the left you have the Andes. You see that we are not exactly at what was the input value, which are in red, but that is to be expected because we are recovering a 3D structure with just a 1D model. But we are very good. We are at a few meters, 100 meters per second away from the real value, and the width of the super rotation is perfectly recovered in a very simple model. On the other case, with Spiru, what you see is that you are creating, so you are completely wrong in terms of rotation and super rotation, and we are creating a degeneracy between rotation and super rotation because Spiru is not able to really see the shapes of the lines. It's just able to see the amplitude of the shift. And so what you have is basically that rot plus super rot is equal to 11,000 in both cases, but Spiru don't know how to go to 11,000, whereas Andes has a very simple solution. And that's interesting because we really have a degeneracy at low signal-to-noise ratio that is lifted by going to high signal-to-noise ratio on the dynamics. And this translates very well into the rotation kernel. This is what is recovered by Andes. So you have the kernel as a function of the Doppler shift. And you see the rotation part in the middle with the two humps and then the super rotating peaks. And Spiru just sees that you need 3 peaks, but it doesn't know how to get to these 3 peaks. And it just depends on what is your posterior and your assumptions. So this is published. I didn't put the paper in the Palais et al. 2023 paper about the science of Andes for exoplanets. All right, so that's my conclusion. What we wanted to do is really try to understand the limits of our retrievals. And as I advocate, I think that we would need to do that more because there are not many simulated papers on what we can really understand from data. And we have done some simple stuff so far, and we are trying to go to see more deep stuff, but that takes time, of course. And I can't wait for Andes to be on Sky and really lift some of this degeneracy, at least in the dynamics. So, thank you very much.
Hello. Can you all hear me? Oh, there we go. Okay. Good morning, everyone. My name is Jorge. I am a rising fourth-year PhD student at Arizona State University. And I'd like to thank the organizers for giving me the chance to speak today, but I'd also like to preface with an apology, saying this is not the title of the talk that's in the program, but I promise I'm still talking about WASP-189. Just a little bit different focus here, in particular, using ultra-hot Jupiters like WASP-189 as laboratories for rocky planets, in particular trying to use the measurement of refractory species like Fe, Si, and Mg that can be measured in their atmospheres. Now, you might be wondering, hey, I haven't seen this guy around this conference, and that's because I literally wasn't around till yesterday. On Monday, I was observing at Keck in Hawaii, and I love exoplanets so much that I wanted to come right from my observing in Hawaii all the way to Germany. So right on the bottom right there is a little bit of my itinerary. Crazy, I know, but I did it just so I could give this talk, but also get a fun picture in front of Gemini North. And if you stick around to the end of the talk, you'll see an even a funner picture with me and a future upcoming instrument on Gemini North. In the spirit of the Two Horses talk, I wanted to give you a little diagram of how my 20 plus hours of traveling went. Something like this. And then a jet lag sets in, a little twist here and there. And so I'm kind of 12 hours behind. So if I say something weird, we can blame the jet lag. But moving on, I want to first just mention sort of the role of the composition of rocky planets and what they can tell us about the interior structure, the evolution, thermal evolution or surface processes on terrestrial planets. In particular, features like mantle composition and mantle mineralogy, what the mantle is made out of, and things like core mantle mass ratios are governed by three main bulk refractory species found in the protoplanetary disk, and that's Fe, Si, and Mg. And I wanted to say these are also really important because sort of understanding the composition, interior structure, surface processes, geological evolution, it affects whether planets might have things like core convections or plate tectonics, like you're seeing on the left and right, this diagram here, and that's or whether they have silicate-rich mantles, and that's really going to differentiate between whether we think of planets as Earth-like or not. But so, okay, well, these things are important. Can we measure them? And the answer is kind of no. For refractory materials locked away in the rocks and terrestrial exoplanets, they're inaccessible to direct measurements. And so there are ways that you can try to estimate the internal composition of an exoplanet through measurements of its density, like through mass and radius constraints. But a lot of those are also degenerate with different kinds of interior compositions depending on what you use for different core sizes or core mantle ratios. So what's most typically done is planet formation models and disk models using adopting the stellar values as the values of Fe, Mg, and Si in the planet. And what you're seeing on this figure from Unterborn 2019 is the Fe, Mg, and Si abundances in a number of Hypatia stars and calculated core mass fractions for different sized terrestrial planets when those planets would adopt the stellar values of Fe, Si, and Mg. So this is something that people do in order to try to estimate what the interior structure and composition of planets, terrestrial planets, might be. But are they really a good proxy for rocky composition? And one of the main reasons people use the stellar values is because that's kind of what we see in the solar system. So, for example, the Mg to Si ratio of the Sun is pretty similar to that of the Earth and for different meteoritic bodies in the solar system. So it's a first order, a good assumption to make. But can we actually use any direct measurements of planets with larger atmospheres like gas giants to test this? Well, as we've heard a little bit about in this week, these species like Fe, Mg, and Si condense out and are not available to be analyzed by spectra in most, the temperatures of most exoplanets. But everybody's favorite now, ultra-hot Jupiters. So this sort of ultra-hot Jupiter opening or opportunity, which allows for the measurement of these planetary building blocks to be in gas phase. So pick your favorite ultra-hot Jupiter, WASP-76, measurements of FE and MG, WASP-121, FE and MG, and then WASP-33, FE and SI. So these kind of species have been found and are continuously found on these the hottest exoplanets in the gas phase through transmission or emission spectroscopy. And I promise, if you're a WASP-189 person, that I'm showing those plots soon. But most of these have been done in the optical. That's where a lot of the lines for these species exist. But we've heard a little bit from Fabio and from Stefan earlier this week about detections of refractory species in the near infrared, and in particular in the H and K band. And what's nice about that is, while there are fewer lines, you get water and CO for free in the H and K band, and so who doesn't like something for free? And so that helps put an even better constraint on the internal atmospheric composition of the planet when you can get the refractory species as well as water and CO in the near infrared. And so, okay, if we want to measure refractory species in ultra-hot Jupiters, we want to do it in the near infrared, what are we going to do? Well, you might have heard a talk from Mike the other day about measuring the thermal emission of a number of hot to ultra-hot Jupiters with his Igrins LLP, which is perfect because Igrins is H and K bands, and in the program we had a number of ultra-hot Jupiters that we observed. In particular, the hottest one right here, WASP-189. Now, WASP-189 has been well studied in the optical. A lot of great work has been done by Bibiana Prinoth to detect many different refractory species in WASP-189. And we know that we've seen these species exist, and we've detected them in multiple instruments. So we know that they exist in WASP-189, and but again, this has been done mainly in the optical. We want to move towards the near infrared to see if we can detect these as well. And so here are observations with Igrins, H and K band. On the left, you'll see Igrins where it used to be on Gemini South. It's no longer on Gemini South. It's moved back home to Texas. Hopefully live out a good life there. And we observed 2 nights with WASP-189b in pre and post eclipse, and so you can see some of the sensitivity of our data here. And with many of our models in the near infrared, when we expect the major opacity sources to be water and CO, we first use a cross correlation. We cross correlate first with a template of mainly volatile species like water, CO, and OH, where we expect OH because of the association of water in this ultra-hot Jupiter, and we get a nice detection of the planetary atmosphere with those species in it. But who cares? We expected this. What if we wanted to look at the refractories, right? I've been talking about it the whole time. Well, if I add refractory species into here, whoa, we see an increase in our detection significance, pointing towards the importance of these species in the atmosphere of this planet. Now, you might be asking the next question: what species did you add in this model? What refractory species, and did you search for them individually? And the answer is yes. Mike gave this away a little yesterday, but we see many species in WASP-189b in the near infrared, including refractories and volatiles. Now, this is really exciting because, like I mentioned before, we've gotten many great studies on the refractory detections, but now we can place detections on refractories and volatiles using the H and K band. And so I'm going to repeat a line you might have heard a few times this week. Motivated by our detections in the cross correlation, we want to move towards sort of atmospheric retrieval land, and to do that, we perform atmospheric retrievals using equilibrium chemistry. And what we find is we're able to place constraints on eight elements in WASP-121b, and I'm plotting here their abundance relative to solar in black, and in red, the same abundances relative to solar for the star, WASP-189 from Lindell 2020. And on the right, you see a calculated metallicity in C to O, particularly a depleted metal polar planet with about a solar C to O. And what I really wanted to focus on now, as I mentioned before, is the detections of Mg, Si, and Fe. So here I'm plotting Fe to Si ratio and Mg to Si ratio relative to log stellar, meaning that a value of 0 would be that it has the same Fe to Si or Mg to Si as stellar. And so you can see that the Fe to Si, we retrieve it to stellar value, but the Mg to Si is depleted. That's interesting. I'll get back to that in a second, but first I want to contextualize the result of WASP-189b in that typically Mg to Si ratios have been calculated for astrophysical objects like polluted white dwarfs or the Earth, the Sun, and as well as solar system meteorites. But we can put the first measurement of a Mg to Si ratio in an exoplanet atmosphere, which is really exciting. So I told you earlier that the Mg to Si ratio has been assumed to be stellar for planets, but we're seeing one that is discernibly not stellar. So what's up with that? Well, I provide you two explanations. The first is from TIBA 2015, which they suggest that while Fe to Si and Mg to Si should be condensed throughout the disk, meaning through most of the disk, meaning that their ratios should be stellar, in the interior of the disk, where those species haven't condensed yet, where it's still hot enough that they haven't condensed, they could be non-stellar in nature. And next, there's when I said the solar system meteorites are all solar, I kind of lied as well, because while carbonaceous chondrites have been found to be close to the solar and Earth values, non-carbonaceous chondrites have been shown to be depleted in Mg relative to the Sun or to the Earth. And Morbidelli 2020 suggests that this might be due to the accretion of magnesium poor planetesimals, offering an explanation of how something in the same sort of disk can be have a different Mg value than its host star. So maybe that's something to consider as well. And so I'll leave you with all these conclusions because I think my time will be up soon. But I also wanted to quickly say another cool thing I had to see at Gemini North. Behind this tarp is Igrans 2. So we're all very excited about that, and it's the cool science that it can do. So stay tuned for that in the coming future, and I'll leave you with my concluding slides. Thank you all so much.
Esparza-Borges from Canarias.
Thank you very much. Good morning, everyone. As you said, I am Emma Esparza-Borges from the Instituto de Astrofísica de Canarias. I am a PhD student there. And today I am going to talk to you about our work on exoplanet atmospheric studies applying cross-correlation techniques to JWST data. So I am focusing on the elephant. I hope you remember the original logo. And we focused our analysis on the exoplanet WASP-121b. WASP-121b was observed for the very first time with JWST in the context of the early release science program. And if you remember, the very first science results from these WASP-121b observations were published in Nature in 2023. And these results came from the observations of 3 different instruments with 4 different observing modes. And I would like to bring your attention to the results from NIRSPEC, specifically from the PRISM and the G395H GRISM. So the results from these observations were published in these 2 articles here. The article on the top are the results from the NIRSPEC PRISM observations. And what the authors saw here is that they were able to detect carbon monoxide with enough confidence among other molecular species such as carbon dioxide and water. But, however, on the results of the NIRSPEC G395H GRISM, which has higher spectral resolution, the authors were not able to detect with enough confidence carbon monoxide. They were able to detect these other molecular species such as carbon dioxide and water. So in this context is how we started our analysis, our cross-correlation analysis on these WASP-121b observations, and we decided to focus on the NIRSPEC G395H dataset. So we aimed to confirm the carbon monoxide detection that the authors saw in the NIRSPEC PRISM results, and we wanted to do this with a higher spectral resolution dataset coming from NIRSPEC G395H. So what we did is to take these JWST observations, we reduced them with a Tiberius pipeline, and we did this at pixel level to keep the spectral resolution as high as we could. And then we decided to focus for the cross-correlation analysis on this portion of the transmission spectrum from 4.6 to 5 microns. And this is because here is where we expect carbon monoxide to dominate over other molecular species such as carbon dioxide or water that we expect to be present in the atmosphere of WASP-121b. So as I already said in the beginning, what we want to do is a cross-correlation analysis. We are doing a cross-correlation analysis as an alternative way to detect carbon monoxide. And to do this, we need to generate first templates of carbon monoxide. And to do this, we started from carbon monoxide line lists that we obtained from the HiTem database, and then we produced atmospheric models of a planet with the characteristics of WASP-121b using Petit Retrans code. And I would also like to highlight that we did 2 templates in parallel. First, we did one that came from the line lists, came from a line list from HiTem that contained only lines for the carbon monoxide main isotopolog. And then we also did a second template that was generated from a line list that contained all isotopologs of carbon monoxide. Then, as I already advanced, we produced the atmospheric models with Petit Retrans. We did several assumptions to do this. Of course, we considered a planet with the characteristics of WASP-121b. We considered that the atmosphere was composed only by carbon monoxide, and we used the line-by-line radiative transfer mode in Petit Retrans that is providing a very high resolution output. And we also assumed, of course, the planetary parameter, the radius, the planetary radius, the surface gravity, and we also assumed an isothermal profile. So once we have generated the atmospheric models that are the plots that you can see on the top, on the left, on your left, you can see the atmospheric model for carbon monoxide main isotopolog, and on the right you can see the atmospheric model for all carbon monoxide isotopologs. Once we have generated this, as you can see, at very high spectral resolution, we need to resample these models in order to match the resolution of our observations. And then we just fit for fourth order polynomial, and we subtract it in order to normalize and generate the templates. So with the templates in hand, we are ready to perform our cross-correlation search. And the cross-correlation procedure that we followed is pretty standard and pretty simple. We just use a cross-correlation function from Pi Astronomy. We shifted the template over a range of plus minus 1,000 kilometers per second using a 6 kilometers per second radial velocity step. And as you know, what we obtained as the result of the cross-correlation is a cross-correlation function that is in cross-correlation values, but we converted these values to signal-to-noise ratio in order to understand better our results. And these are the resulting cross-correlation functions that we obtained. On the left, you can see the cross-correlation function for the case of the cross-correlation with the template of the carbon monoxide main isotopolog, and on the right, you can see the case for all isotopologs. As you can see, in both cases, we have a detection, we have a central peak that is shifted towards minus 80 kilometers per second, approximately. And this is totally fine because this is consistent with the systemic velocity that we expected for WASP-121b plus the JWST velocity at the time of the observation. So first result, we are able to do a detection of carbon monoxide with JWST and cross correlations. And then another thing that we try to understand better in our work is that we are not only seeing this central peak, but we are also seeing that this central peak is surrounded by secondary peaks around plus minus 600 kilometers per second. At the very beginning of our analysis, we didn't know where these peaks were coming from. So we decided to perform let's call it the self-correlation of the templates with themselves. So we cross-correlated the carbon monoxide template with itself, and also we did the same but with the data. And what we obtained is that the secondary peaks are present in the self-correlation of the template with itself. So the presence of the secondary peaks is coming actually from the carbon monoxide signal, and we think that this fact is actually reinforcing our carbon monoxide detection. And another thing that I would like to highlight among our results is that the significance of our carbon monoxide detection is slightly increasing when we are taking into account all isotopologs in the carbon monoxide template. As you can see, this increase is very slight, it's only around 1 sigma, but we think that this is a hope for the future, that this technique might have the potential in the future to perform the search of individual isotopologs. And these are the conclusions of our work. As I have already said, we were able to detect carbon monoxide in the atmosphere of WASP-121b with JWST near-spec G395H data. That is the highest spectral resolution that we can get with JWST. And I would like to highlight that we did this using standard cross-correlation techniques. So the message that I would like you to bring home is that cross-correlation techniques are a new pathway that has been opened in order to analyze JWST data and in order to perform atmospheric studies. And in comparison with the traditional retrieval techniques and analysis that are frequently used, this is a technique that is computationally very cheap compared to that. So that's the message I would like you to bring home. And thank you very much for your attention. Here I am leaving a QR code that will lead you to the article. And just in case you want to check the details, of course, feel free to contact me if you have any question. And I will be also happy to take questions now. Thank you very much.
Okay, welcome back, everyone. Please take a seat. We are starting imminently. Okay, welcome back for session 2. I'm Jane Beckby. I shall be your host for this session. Looking forward to all of your questions. We have 6 talks, so we will get started with Ruizhe Wang, who's going to tell us about a multi-dimensional high-resolution retrieval with POSEIDON.
Okay, thanks. Before I get started, I thought I should introduce myself. My name is Ruizhe Wang, and I just graduated from Cornell in astronomy. Bachelor degree in astronomy and computer science. And in the fall, I'll be moving to California Institute of Technology for a planetary science PhD program. And so this is my undergraduate research project with Dr. Ryan McDonald, who developed POSEIDON. So just based on the title, we have so many questions that we could ask. For example, what is POSEIDON, and so on. So let's just start by asking, what is POSEIDON? Wikipedia tells us Poseidon is the god of the sea, storms, earthquakes, and horses. I did not know about that. And also on Wikipedia, here's a drawing of Poseidon riding 2 seahorses. There are also horses. It's not AI generated, it's actually from the 3rd century and stored in a museum somewhere in Medina, Tunisia. I thought that's very interesting. But Poseidon in exoplanet context is an exoplanet characterization tool written by Dr. Ryan McDonald that has both a forward model and a retrieval framework combined with it. And for the retrieval, we use nested sampling, and the forward model has both transmission radiative transfer and emission radiative transfer. And for the multi-dimensional part, it's mainly, for now, it's only transmission. And the forward model is called Trident, which you can see here, Poseidon holding a trident. And the second question we could ask is, why do we do open source softwares in general? And for me, as an early career scientist, I've learned so much from these 5 tools that I've used in my short career, that is 1.5 years. And I've learned so much from them. And the second reason is it's good for new sciences. For example, just take a look at how many people have used petit retrans in this conference. Raise your hand if you use it. Wow. And the third question, the third point is, let's not kid ourselves. It's for the citations. Look, 300. And just to acknowledge other codes that serve the same purposes that I've either referred to, or they came out after I read my code. They're listed here. And it's cool to see how they go from a Dropbox links in a paper to finally GitHub with documentation. So the third question we should ask is, why high resolution spectroscopy? And for that, we could refer to Sid Gandhi's talk on Tuesday. I really enjoyed it. And just to reiterate a few things. First, high-res spectroscopy is complementary to space-based telescopes because, as we heard from Tuesday, it is more sensitive to individual lines and line contrast and line shapes as well. So they're good for relative abundances, but not so much for absolute abundances and temperature pressure profiles, which come from the continuum information. And we've also heard so much about atmospheric dynamics and how we could get it from high-res observation. And one point we haven't touched yet is there are so much more observing opportunities on the ground than in the space. And here's a non-exhaustive list that I've compiled for my upcoming paper of every or most high-resolution spectrograph currently available that has been used for at least one cross-correlation analysis. And just look at it, all over the world and a wide range of wavelength coverage and different resolutions. So I think it's a fourth question we could ask is why multidimensional? So despite people who want to ignore it, it's intrinsically 3D. It may have day-night variation and length asymmetry, and also maybe there's patchy cloud coverages, etc. And with a multidimensional model, you could actually link back to atmospheric dynamics instead of just looking at the 1D chemistry abundances. And for that, I should refer to Haley Bell's, Peter Smith, and Fabio Lesjac's talk on Tuesday. So let's talk about POSEIDON's forward model Trident. Here's a nice paper in 2022 from Dr. McDonald and Professor Louise. She's my academic advisor at Cornell. So to do a 3D parameterization of temperature as well as chemistry, we need 4. Here we used 4 free parameters, and the four of them are: first, the temperature deep down in the atmosphere, and second, the mean temperature of the terminator, and 3, the difference in temperature between the morning and evening terminator, and 4, the temperature difference between the day side and the night side. And with the 4 parameters in place, you could linearly, linearly interpolating all the temperatures between these points, sort of say. Okay, and on the right is the animation of how the 3D map may look like with a day-night temperature difference. And we are parameterizing composition in the same way. So for each species, you could have at most 4 parameters, but you could also just use 1, like an isochem. And we've seen and heard so much about how a 3D model will bias your result, and how a 1D model will bias your result. And we can see this from this 2022 paper that day side, night side temperature difference as well as chemistry difference can lead to change in transmission spectra. And on the first graph on the top left shows us a pure day-night temperature gradient increases the amplitude of those transmission features, which we can see here. And notice the residual, like the difference is about 250 points per million at the maximum. And on the second plot, we can see, first of all, it's a pure day-night composition gradient, so the temperature between in the day side and the night side are the same. And in that case, we have actually a symmetry between a positive composition gradient and the negative composition gradient, because if the temperature is the same, that you can just interchange the day side and the night side, and the total optical depth is the same. And we can see that from here. There are only 3 lines. That's because 2 pairs overlap each other. And on the third plot, on the in the bottom right, shows us when there is a temperature difference between day side and night side, there's more change or a larger change to the transmission spectra, and the symmetry also breaks. So I've run a simple injection test. This is a 2D transmission model with day side, night side, temperature difference, and chemistry difference only. So I didn't include the morning terminator and evening terminator difference. And we can see from this injection test, it would be difficult to probe these gradients, especially the composition gradients without proper temperature constraints. And for that, we can see here, there's a degeneracy between positive gradient and negative gradient, which makes sense because when there's no delta T between day side and night side, their effect on the spectra would be exactly the same. So it would be hard to break that degeneracy without proper constraints, but I figure we could get that from space-based observation and run a joint retrieval maybe. That's for the future. but for now, I've also run a 2D transmission model, so similar to the injection test I ran before, on the UV's observation of WASP-121b, and this planet and this data set has been studied in many papers, like Gibson et al. 2020, 2022. And what I found is, wait, I should zoom in first. What I found is I've noticed a similar thing that in the injection test, that there's this symmetry, but also for iron, this symmetry is not there. I don't know if we could call this evidence or anything, but if you have any idea, you could talk to me later. Yeah, but this is very preliminary, and I'm looking forward to testing it further. Okay, last point I want to make is the trending makes a difference. This is on the WASP-121b I-grains emission observation. So the one I get from Line et al. 2021, the Dropbox link, and I run 2 retrievals, one with PCA and one with SysRAM, and although the mean values is pretty consistent with the previous studies, the SysRAM gives a broader constraint than the PCA, and I speculate, it's just a speculation, it's because PCA assumes uniform noise of your data set, whereas SysRAM, it needs to estimate your time and wavelength dependent noise before, so PCA may be more optimistic in your data set. Thus the smaller standard deviation. Oh, this is actually the last point, is you could and you should relax your parameterization when possible. And here's an injection test with transmission signal with a temperature gradient, and I retrieve it with either with 2 models. One is isothermal and the other is the same parameterization. And you could see that they don't disagree like at all. And what is cool about it is, well, I don't think it's cool, so yeah. And the reason here is transmission spectroscopy is less, at high resolution is less sensitive to temperature gradient. So we could sometimes maybe use isothermal profile instead of a parameterized one to save some time. And there's a conclusion in Hogg and Foreman-Mackey 2017. They said number of samples grow exponentially with the dimension, so it saves you a lot of time. And finally, who and why should we care, or you care? First, we have validated this with previous studies on a lot of planets, and our code is fast thanks to fast filtering method by Gibson, and nested sampling, as well as POSEIDON's fast-forward model that is Trident. And second, we are preparing, namely I am preparing documentation and tutorial notebooks for both emission and transmission high-resolution spectroscopy, so you could run retrievals or cross-correlation and make those plots. And it is Git installable. And finally, you could maybe reference it when writing your own cross-correlation code and maybe cross-reference, so make sure no one's doing anything incorrectly. And thank you.
Thank you. Next speaker is Joost Wardenier, who's going to bridge the gap between theory and observations.
Hello everyone, good morning. My name is Joost. I'm a postdoc at IREX at the University of Montreal. And today I'll talk a bit about IGRIN's observations of the ultra Jupiter WASP-121b that we observed in transmission. I'll try to interpret these data in the context of 3D atmospheric models of these ultra Jupiters. So I think after all the fantastic talks we've seen this week, ultra Jupiters don't need any introduction anymore. For the sake of completeness, I would like to mention some of the parameters of WASP-121b. It's really this canonical ultra Jupiter with a period of about 1.3 days and an equilibrium temperature of about 2400 Kelvin. And arguably it's one of the best characterized exoplanets to date. Using high-resolution spectroscopy, about 20 chemical species have been detected in its atmosphere. I think for many of these species we'll also have constrained abundances, which is going to be great. Of course, WASP-121b has also been studied extensively from space, most recently through a James Webb phase curve. So, as we all know, these ultra hot Jupiters are inherently three-dimensional, and of course this is relevant when we look at the phase curve of the planet, the emission spectrum. But the point I want to hammer home here is that when we look at the transits of these ultra hot Jupiters, it's also very important to take into account the 3Dness of the planet, which is illustrated here on this slide. Because the thing is that ultra hot Jupiters, they rotate by about 30 degrees as they pass in front of their star. So this means that at different phases during the transit, we're really probing different parts of the atmosphere. So you can see here that as we go from ingress to egress, you can see that we first probe the day side of the atmosphere on the leading limb, but then as the planet rotates, the day side rotates out of view, and the day side rotates into view on the trailing limb. And of course, this effective temperature profile that we're seeing also affects the effective abundances, in this case of iron, for example, that we're seeing in the limb plane, and also the effective Doppler shifts across the limb that are set by the rotation of the planet, but also the wind profile, which mainly consists of the day-to-night flow and potentially an equatorial jet. So some observations that really beautifully demonstrate this 3D structure of ultra Jupiters are shown over here. We've seen these cross-correlation maps multiple times throughout this week. So here we're seeing the Doppler shift of iron in transmission as a function of orbital phase during the transit. And you can see that this Doppler shift is not constant as a function of phase, but it shows a certain behavior. And this really encapsulates a lot of physics about the way iron is distributed across the atmosphere, about the wind profile of the planet, clouds, asymmetries between the trailing and the leading limb. So there's a lot of physical properties to be inferred from these trills. And I think Adrien in 2 talks will also tell more about what we can say from these iron trills. So sort of I think the question that motivated our observations was to see whether we can also produce these absorption trills in the infrared, which mainly targets water and CO. And the sort of rationale is that water and CO have different spatial distributions throughout the atmosphere compared to iron. So that means that if we compare the cross-correlation trills of these different species, we get complementary information about what's happening in the atmosphere in terms of the 3D structure. So this is where IGRINS comes into play. IGRINS is a high-resolution spectrograph on the Gemini South telescope, and it beautifully covers this wavelength range between 1.4 and 2.4 micron. We targeted WASP-121b 3 times in its transit. So these are the absorption trills that we obtain. For CO, for example, you can beautifully see this diagonal trill of the planet, which is due to the orbital motion. For water, you can also see a trill within the dashed lines, although it's slightly more faint. And then in the bottom row of this plot, the trills are transformed to the planet rest frame, where they are centered around 0 kilometers per second. So because we're at a high-resolution conference, of course, I can't get away without showing the KPV-SIS maps of the detections. So you can see here that CO and water, the peaks are slightly shifted compared to where we expect them to be based on the orbital parameters of the planet. Interestingly, we don't really find any strong evidence for OH. I mean, there is a sort of like very faint structure about the expected planet position, but this is not a significant detection. It might be that the region that we're probing with our transmission observations, just doesn't contain enough OH. But the fact that we're seeing these shifts in the KPV sysmaps is very encouraging from a 3D point of view, because it means that the CCF trail that I showed on the previous slide, it must deviate from 0 kilometers per second in the planet rest frame. So in order to measure this deviation, I binned the trails into 4 bins basically across the transit, and then I fit Gaussians to the cross-correlation peak to figure out what the effective Doppler shift is of the signal, and you can see the results over here. And basically what the different colored lines show is the different number of SVD or PCA components that are removed from the data during the reduction. And you can see that it doesn't really matter how aggressively you clean the data, we always wind up with a similar qualitative trend. So we can see that the CO lines, they get increasingly blue shifted throughout the transit, but water on the other hand gets increasingly red shifted. The question is, why is this? How can we explain this? So in order to do that, let's look at the equatorial plane of WASP-121b. I'm plotting here the distribution of carbon monoxide throughout the atmosphere. You can see that it's very uniform because carbon monoxide doesn't really condense out, it doesn't really thermally dissociate. One limb of the planet will be blue shifted because of the rotation, and the other limb will be red shifted because it's rotating away from the observer. So if we zoom in on the evening terminator, for example, you can see here 2 regions, a blue region and a red region that I'm plotting. The blue region is the region that is probed by the line core of CO, and the red region is the region that is probed by the continuum. And basically the strength of the cross-correlation signal, or the line, it's sort of set by the physical distance between these 2 regions, where the line core is probing and the continuum is probing. And then when we make this plot as a function of orbital phase during the transit, so the planet rotates, you can see that at the start of the transit, the sort of the projected distance between the region probed by the line core and the region probed by the continuum is smaller than towards the end of the transit when we see more of the day side. So this actually means that a line associated with the evening terminator will get stronger throughout the transit. And this is the reason why for carbon monoxide we see this increase in blue shift, because initially at the start of the transit we're seeing more of the morning terminator, which is red shifted as it rotates away from the observer. But then as the day side rotates into view on the evening terminator, we start getting this increase in blue shift. Now for water we can play the exact same game. The difference between water and CO though is that water is thermally dissociated on the day side of the planet. So it means that our observation will mainly probe the night side, which is also what you can see when we plot the regions probed by the line core and the continuum again. They now lie on the night side. And again, when we make this plot as a function of orbital phase throughout the transit, you can see that on the evening terminator at the start of the transit, when most of the night side is in view on this side of the transit, on this side of the planet, the regions are relatively far apart. But then as the planet rotates, the absorption regions are pushed towards the day side, where there's a gradient in the water abundance. And the region probed by the line core and the region probed by the continuum, they move closer together, so that the absorption line associated with this part of the transit is very weak for the evening terminator. So this is an opposite effect compared to CO, and this is also the reason why water probably becomes increasingly redshifted throughout the transit. I think as a sort of like conclusion, we can say that the change in Doppler shift that you see for these different species, it's really driven by how a molecule is distributed throughout the atmosphere, and then in combination with the day-night temperature contrast of the planet and the rotation during the atmosphere, you get these different trails. So then in the last few minutes of the talk, I would like to draw a comparison with trails that we compute from global circulation models. So we took 4 different global circulation models of WASP-121b. We post-process these with a 3D radiative transfer code, which basically simulates a spectrum at different orbital phases throughout the transit. With the code, we can account for Doppler shifts that are imparted on the opacities by winds and by planet rotation. And then when we do the cross-correlation for each of these spectra, we get theoretical cross-correlation maps. So the results of those simulations are shown over here. The great thing about WASP-121b is that we now have absorption trails in the infrared for CO and water. But also we can make a comparison to the previously published iron trail from Borsa et al. in 2021. So the data points here are the trails that are measured and observed, and then the colored lines are the outputs from the GCM. Of course, there is no perfect match, but we can draw we can draw certain qualitative conclusions about what might be happening in this atmosphere. What's interesting to see, first of all, is that there's only one model that really fits the water signal very well, and this is a model which has very strong drag, which means that the winds and the GCM are very slowed down. And when this is the case, like the rotation really dominates the Doppler shifts that you're getting. And also for CO, we can see that the best qualitative fit is given by GCM that has drag in it. What's interesting to see for iron, for example, is that the red line, which is the best fit to the water model, it doesn't really fit the iron data very well in all parts of the transit, which probably indicates that iron and CO are probing different parts of the atmosphere. For iron, we probably need slightly less drag to get a better fit to the data. Then the last thing I want to briefly touch upon is the water signal of the planet. So as I was showing previously, the signal seems to be muted at the start of the transit. This might well be due to telluric effects, but we can speculate, of course, if this is physical, what might be going on in the atmosphere. And in the paper, we find that if we include some sort of opacity deck or cloud deck on the evening limb of the planet, we can mute the signal in this first part of the transit. So I think this definitely needs like follow-up observations to confirm what exactly is going on in the atmosphere. So yeah, briefly going to the conclusions. So with Gemini South Igrins, we've shown that we can really phase resolve these absorption signatures of water and CO, which is very exciting. They provide complementary information about the 3D structure of the atmosphere. We find that the data generally need atmospheric drag to be explained. This is also in agreement with phase curve observations from James Webb, for example. And we can probably explain this muted water signal by including some clouds on the evening terminator of the planet. And then the last thing I want to do, because I realize I'm almost over time, is to once again draw your attention to exoclimbs in Montreal next year. So you can talk to Romain or Vignesh or me if you want to know more about this great conference that we're organizing next year. Thanks a lot for your attention.
Okay, next up we have Arjun Savel, who's going to tell us about 1D on 3D.
Thank you very much. Yes, my name is indeed Arjun Savel. And I put up this beautiful iridescent rotating horse to kind of motivate the idea that I think we lose some of the beauty of atmospheres when we compress them down to 1D, right? This horse is now very sad, it's very tiny. It's still rotating, sure, but it's not what it could be. Yeah. So, I'm glad that people at this conference are also starting to appreciate this as well. Some of the 1D modelers among us are starting to begrudgingly admit that atmospheres are not, in fact, lines. Some of them, in fact, are spheres, and that could potentially impact some of our data. And I'm particularly glad to hear that because I've developed a bit of a reputation in my own department as the guy who won't stop talking about how atmospheres are spheres. And all the people outside of exoplanets think that's really funny, so I've been gifted a plaque that commemorates this as the local orb ponderer in my department. But the question, of course, isn't whether atmospheres are actually three-dimensional, right? It's a little silly. The question is whether atmospheres are three-dimensional in ways that actually matter, that we care about. And now, if you allow me to get, here, I'll just click. If you allow me to get a little bit philosophical, right? What is mattering, right? What does it mean to actually matter as a concept? If you are an excitable theorist like me, maybe it's cool physics, right? Maybe you're looking for 17th order effects in this atmosphere. You want to hear the clopping of hooves on some rocky surface or something, right? But if you want to be a helpful theorist to your observer colleagues, you want to be a little bit more data-driven, right? So this question reduces to something a little bit more concrete. A couple related concepts. One, are more complex models preferred by our data sets? And number two, the thing that I'll focus on a little bit more, does underlying complexity actually bias your simpler models? And for the high-res community, we've had these 3D effects knocking on our door for quite some time, right? So you can go back 4 years ago when I had perfectly working eyeballs, the Ehrenreich et al. 2020 paper, right? We can see that something is changing in the atmosphere, right? Or you can roll back to 4 minutes ago for Joost's great WASP-121b work, and we can see that things are changing in the atmosphere, right? So chemistry, winds, temperature, clouds, these spatially varying quantities are certainly impacting our data to some degree. And this might sound like a familiar story, right? We've been hearing about these three-dimensional effects on 1D inference for years from our lower resolution colleagues, right? We've been studying 3D biases on 1D retrievals at JWST level precision for years now. So the tricky thing that I find a little bit concerning is that we might actually be more susceptible to 3D biases with high-res data. The reason being, we have sensitivity to wind fields, right? When we fully resolve our lines, even if they're below the noise level, we're sensitive to line shapes that can be perturbed by dynamics fields. So the goal of this study is to try and assess whether our inference methods are swayed by these 3D effects, right? And practically what that means is performing one-dimensional retrievals on simulated 3D atmospheres. So to begin, I start with some three-dimensional atmospheric structures. So this could be a GCM, for instance. And I do want to mention that I myself am not running the GCMs. My brave GCM colleagues will march into the dark forests by themselves and return with the GCM like 3 weeks later. And I'll like be an armchair dynamicist and say, yes, Rossby waves or something. So I'm not running them myself. That's the beginning of my study. And then I move on to my own personal bread and butter, the 3D ray-striking radiative transfer, right? So I take this GCM, I post-process it, and create a spectrum that's informed by the Doppler shifts in the atmosphere, by the spatially varying chemistry, temperature, et cetera. And then I perform what I lovingly refer to as datification, right? I make these models look a little bit more like data. I sprinkle some photon noise on top, I paste a star, tellurics, instrumental response, things like that. Perform PCA. So make it closer to an actual comparison with what real inference would look like in real life. Then I create my 1D spectrum, I cross-correlate, and I do a retrieval, which hopefully has posteriors that look a little bit better than that. But I do want to mention that for this study, it's actually not these different boxes that are the hard part for me. I already had these ingredients lying around my kitchen. The tricky thing was making them all play nice with one another. So I want to emphasize that the arrows are actually the hard part of this study, making these different inputs and outputs couple nicely. I will also mention that the study was made quite a bit easier by a method that I developed earlier this year to compress my opacities by about an order of magnitude. So if you are worried about all the space that you can't fit onto your GPUs and you would like to squeeze your opacities down by like a factor of 10, scan the QR code, polynomials, machine learning, all that kind of fun stuff. So in addition to the three-dimensional atmospheres, right, if I perform my 1D retrieval on the GCM, and I get some answer that's not what I expect, it's kind of hard to disentangle exactly why that is. Kind of the beauty of GCMs is that they have a lot of physics baked into them, right? So I also undertook this idea of paring down some of the complexity of these 3D atmospheres. So creating these simplified 3D structures that aren't actually GCM outputs, but kind of look like them. And I split them among 3 different axes, so temperature, chemistry, and dynamics. And for instance, for temperature, I'll have just a nice little isothermal blob, or I'll vary by latitude or longitude or day to night contrast, right? Chemistry, we can include just water on one side of the planet and CO all around. Or I can have water vary by equilibrium chemistry, so it's not just on one side, but it still changes a little bit from latitude to longitude to altitude. In the dynamic sense, we can also rotate the planet under solid body rotation. And I do want to emphasize, subtle difference, this is not quite the same thing as doing a 1D convolutional kernel. I'll come back to this. We can also include some winds. Usually winds look a little bit more coherent than this. And we can include the rotation and the winds. So by performing 1D retrievals on all these different simplified atmospheres, the idea is that we can get some intuition for what types of physics, chemistry, etc., is actually changing our retrieval results. So this turns out to be quite a number of simulations, right? The downside of grids is that you actually have to run them, apparently. So a couple thousand 3D spectra, like 36 retrievals, which is kind of difficult to piece together. But I'm going to try and weave a story that still makes sense. To try and build some intuition a little bit more, I'm going to start by looking at just the 3D forward-modeled spectra. So the fun thing about this is that, I was just talking to Wutzel about this, you go back to Brown 2001, and there's actually a lot of this physics predicted all the way back then. So some of this isn't necessarily new at the spectrum level. It's how these features interact with one another at the retrieval level later on that is particularly interesting. But just to build some intuition, what happens when you vary the temperature spatially around your planet? Well, temperature interacts with transmission spectra via the scale height, right? So you might think initially, I crank up the temperature, bigger feature size, strong absorption lines. That is true. The tricky thing is that not all lines will get stretched or shrunk the same way. Because there's spatially varying temperature that's increasing or decreasing, it's going to affect the lines that become optically thick at different parts of the atmosphere differently. Additionally, the temperature dependence of the actual opacity function is going to be different for different lines, right? So unfortunately, changing your temperature isn't as simple as just stretching or shrinking. Now, when you spatially vary your chemistry, what happens is that you have some kind of stretching and shrinking flavored activity as well, but you also have lines that just wink in and out of existence altogether. So of course, if I deplete water throughout the whole atmosphere, it's just going to go away, that whole set of lines. And finally, when we get to dynamics, this is where things get a little crunchy, right? The line profiles don't look like they used to. They're smeared out in all these really complex and distressing shapes, right? They don't look like the 1D expectations. And I do want to mention, right, this is a very high signal to noise. This is at this point noiseless. This is at a resolution of R of 1,000,000, which we don't quite have yet, necessarily, right? But this is just building intuition for what these different effects are doing. So I don't use this R of 1,000,000 spectrum later down the road. I'm just showing this so that we know what's happening underneath the hood. I'll now point out a couple of my favorite KPV sysmaps. So this harkens back to some work that's been done before. Aaron Flowers, Haley Belts, Joost as well was talking about some of this. When we look at, for HD 209458b, so that's the colder planet in my grid of 2, we see that when we spatially vary the temperature structure in the atmosphere, the detection significance goes down. We kind of expect this. The 1D model can't match perfectly with the underlying 3-dimensional spectrum. And similar-ish things happen when we vary the chemistry around the planet. One thing that I'll note is that the KP offset that we get from just having water on one side of the limb matches quite nicely with what Joost derived, I think, last year. And when we include rotation, winds, this also eats out of this signal. This 18.9 goes all the way down to SNR of 10.4, right? And in this case, rotation does less eating out of the signal than the winds that I pasted on from the GCM. For WASP-76b, the situation is kind of similar. One thing that I'll mention is that rotation eats out more signal now than winds do. Why might that be? WASP-76b rotates more quickly, right? So that rotation effect is stronger. And so finally, the promised retrieval results, right? I'll show one that I'm particularly interested in. So I perform my 1D retrieval on this underlying 3D atmosphere that includes rotation and winds. Everything else is constant, though. Constant abundances, constant temperature, isothermal. And if you look at this, I'm like, okay, cool. I can kind of squint, and that looks Gaussian. Maybe this is converged. That's great. It's bounded. But an eagle-eyed retrieval runner will notice this kind of looks like a ceiling effect, right? And it's actually pushing up against the upper bound of the prior. That's not good. And if I think back to what I actually input for this equatorial rotational velocity, right? So this is 1D broadening kernel. What's the truth that I put in? Oh, it's all the way over there. So what we're learning from this is that this 1D broadening kernel can't quite capture the really complex line structure that's induced when we try to include three-dimensional wind fields, when we try to include solid body rotation at multiple altitudes. So perhaps we need to step beyond our simpler versions of these 1D broadening kernels and move on to the fancier ones, right, that allow different velocities at different points in the atmosphere, things like that. So at this point, you might be thinking, wow, you came and rained on my parade. I don't want to hear any of this. All you did is make me sad. I want science that works. You're not giving me anything actionable to do here. And sure, I will say one thing that is hopefully helpful is that I've been thinking about the types of planets that are best suited for 1D retrievals, right? If you go too hot, there's really fast rotation, there's really fast winds, maybe strong 3D effects there. If you go too cold, your planets are maybe moving too slowly, right, to pick up any real signal from in high res. And around a little cooler than the ultra-hot Jupiter threshold, you might have your maximum actual asymmetry limb to limb. So maybe your good old hot Jupiters are actually the best bet for doing really high signal to noise 1D retrievals, perhaps. So conclusions, I'll just flash them up here. Things get a little bit more complicated than a 1D rotation kernel in the retrievals when you include this spatially varying wind and rotation. These spatially varying quantities can influence our detection significances, and maybe we should go all the way back to our regular standard hot Jupiters to do our 1D parameter inference at its best. And yeah, I will now take any questions.
Okay, so next up we have Adrien Simonnin, who's going to tell us about TOI-1518.
So good morning, everyone. So my name is Adrien Simonnin, as Jane said. So I'm second year PhD student at Observatoire de la Côte d'Azur, and I will finish my PhD in end of September 2025. And today I want to talk about the chemical and wind pattern in the hot Jupiter's TOI-1518b. So as Joost already introduced me, and a lot of people talks about hot Jupiters, I will be brief on that. So why do we observe ultra hot Jupiters? Is because they are big, they are easy to observe. As we use, you can access to refractory elements that are inaccessible in cooler planets, and you can also study the 3D structure of this planet and do some try to characterize them with global circulation model for the day-to-night side or the wind. So Joost already presented that, so I will be fast. So this is an example of WASP-121b detected by Ruizhe et al. So when you see the blue shift, it is a function of the orbital phase, and this effect could be due to the fact that we observe different part of different limb as the transit is progressing. So at the beginning we are observing the leading limb, and at the end we are observing the trailing limb, and so adding the effect of planet rotation and winds, that could create this blue shift that we are seeing. So let me introduce now the ExoWind observational program. So this is a program led by Vivien Parmentier. It's a program for transmission spectroscopy with the instrument MARON-X, so in the visible, and it has a resolution power of 85,000. It's at Gemini North, so 8-meter telescope. And this is a list of all the targets we already observed with one from Peltier's Stefan program. And the aim of this program is to characterize the wind inside these hot Jupiters. So now let me show you a quick look of the results, preliminary results for this planet. So for 8P70b, TOI-1518b, and KEL-20b, we have a clear detection of the iron trace, so that you see in yellow in vertical lines in the planet's trace frame, and in dark is the Doppler shadow. But for the cooler planet, like KEL-7b, KEL-4b, and KEL-11b, unfortunately, for now, we don't have clear detection of the iron trail, maybe because we are polluted by the stellar signal or the Doppler shadow. But for KEL-11b, that is the coolest planet we have, like 1700 Kelvin, we have iron detection in the KPV6 referential. So this is cool and needs more work to do on this target. But for now, let me focus on TOI-1518b. So this planet is orbiting fast and hot stars, and it has a temperature around 2,500 Kelvin and orbital period of 2 days. And iron was already detected by Cabo et al. In 2021. And why this target is critical? Because the planet is near grazing. So as you can see on the left, you see the planet is crossing the limb of the star due to the high impact parameter of the planet. And so this results as a small fraction of the planet for the most part of the transit. So we have only the middle of the transit where the full fraction of the planet is crossing our stars. So now the first step we have to do with the data is data reduction. So on the top is an example of the data, the raw data for MARON-X for one order. So what you have here is strong stellar lines, so it's calcium plus lines, and you have also some telluric and stellar lines. And so what we did is we used the out-of-transit dataset we had to create a stellar spectrum, and then we were able to correct the full dataset with that. So this is what we obtained. And as you can see, we don't have only residuals. In this case, we see clearly the planetary signal in blue, so in absorption. And what you see in emission in yellow is a Doppler shadow of the planet. And so this is really cool because we are able to resolve line with MARON-X, but this is only the case for strongest planetary lines, such as Ca+. If you want to go to highlight weaker signal, we need to see cross correlation. And so that's what we've done. So here I show you the calcium plus. So for the calcium plus, we saw the line directly, and we have a really strong signal in the KPV6 map. We're also able to redetect the iron as Cabo et al. Did, but it is not only the only species we detected. We detected more than 13 species in the atmosphere of TOI-1518b, going from transition metals to ions to alkalines. And so this is super cool, but now that we have detection, what we can do? We can try to infer chemical abundances with retrieval. So that's what we've done. We're using the Chimera code of Michael Lind. So this is a retrieval relative abundances from the retrieval compared to iron and normalized with solar value. So as you can see, vanadium and sodium are consistent with solar value abundances, but for titanium, calcium, and chromium, we are depleted. And so I refer you to the Stefan Peltier talks where he says that titanium is a bit tricky, and so for this planet, we expect it to be depleted. So this is not surprising, and it's quite with the other planet observed with Maronex. So more than chemical abundances, what we can also do is trying to observe the effect of the wind. So I will show you here the trail of TOI-1518b. So you see the trail in yellow, and in blue the Doppler shadow. So we decided to not correct for it because the Rostow-McLaughlin effect does not cross the planetary signal, so it does not disturb us. And so now if we zoom in, you see that the iron signal is blue shifted compared to the if the atmosphere was static. And so it has a pattern that's similar maybe to WASP-76b. So what we can do here is bending the frame and do some Gaussian fit to highlight the signal. And so this is what we obtain after the Gaussian fit. So we see the iron trail blue shifted as function of the orbital phases. So now to try to understand what is happening now, we can use some global circulation models. So Joost already introduced you the global circulation models, but so I used in my case a model of Vivien Parmentier in 2018. So here you have the distribution of temperature in TOI-1518b. So you see that the day side is more hot than the night side, but you can also look at the velocity distribution inside the atmosphere of the wind in the atmosphere of TOI-1518b. And we use two different models, one with no drag effect and one with drag effect. And as Joost already explained, the drag effect will have the impact to reduce the wind inside the atmosphere of our planet. So now with this model, we managed to obtain CCF maps. So here I just highlight the fact that when you do the CCF model and the GCM models, you have to be careful about the impact parameter. So on the top, I show the drag model with the impact parameter equal to 0. So you can see that you're not illuminated the same part as the planet at the beginning and at the end of the transit, as if you use a high impact parameter, as in the case of TOI-1518b, that is shown in the bottom row. And as you can see in the bottom row, the blue shift of the signal is more strong than in the top row without the drag effect. So this is really something we have to take into account. But the GCM models I show here, there is no noise. So what you have to do, if you want to compare with your data set, is to do the injection inside the data and then do some PCA. But if you do some PCA, after the injection and the PCA, what you obtain is two HoRSEs. No. Okay, so what you really obtain when you remove more PCA is this. So we remove the same number of PCA as we did for the data. And so that's what we obtain. So it's modeled really similar to without injection. So it says that the PCA does not impact the position of your, does not impact too much the position of your signal. So now, if we compare with the data, in red is the data of Gaussian fit I showed you before. In blue, it's a no drag model, and in green is a drag model. And as you can see, to explain the blue shift we see in the data set, we need a strong drag effect, because otherwise, with no drag effect, you will have a blue shift that it will be too important due to the winds. So you have to reduce the winds to match the data set. But more comparison than just to the GCM, we can compare different species between them. So that's what we did with I1 and I1+. So here you have the trail of the two species we see in the data set. And so here, if I show the same method of the Gaussian fit, you see that both I1 and I1+ show surprisingly similar trend. So we were expecting the I1+ and I1 to be at different parts of the atmosphere, so maybe having different trail, but it seems that they have the same trail. So we need more work to understand why. And now if we compare to other species, so you have iron, I1+, magnesium, calcium, and sodium, you see that all these species are quite blue shifted with orbital phase. So same, this seems to be at all the same position in the atmosphere. So it's quite interesting. And now, If we go back to the ExoWind program, where I show you the iron detection for the 3 planets, 8P70b, TOI, and KELT20b, we can also compare these trails, so that's what I did. So here you have the trail of 8P70b on the left, TOI in the middle, and KELT20b on the right. And I just show you the geometry of free transit because we saw that it was important. And so as you can see, the 3 planets are blue shifted, the trails. But if you look at in the details, they are all different. 8P70b seems to be less blue shifted than TOI, and KELT20b has not the same trend as the other one. So we need more work again to understand why these 3 planets are different. And now if we compare to the literature, to the previous detection, so this is what we obtained. So we have the 3 planets of the ExoWind program on the top panel, and on the bottom panel we have the 3 planets previously detected, like WASP-76b, WASP-121b, and WASP-189b. And so you see that for the 6 planets, the signal is blue shifted. So this is a common trend of the iron trail for all of the planets, of all the ultra Jupiters already detected. So to conclude, in my work for the transit of TOI-1518b, we detect many species. We measure the planetary trail for iron, iron plus, magnesium, sodium, and calcium. The abundance shows that the titanium is depleted compared to iron, but this is something we were expected. The iron trail that we observe a better match with the drag model, so we need drag to explain the blue shift we observed. And in the end, the ExoWind program detects iron trail with many planets that show the same blue shift, but the same trend of being blue shifted, but they are all diverse, so there is more work to understand this diversity. And so if you have any question or you want to collaborate, don't hesitate to contact me, and I will answer your question now. Thank you.
Okay, so next up we have Daniel Sebastian, who's going to talk to us about what we can learn from binary stars.
Hello everybody. Yeah, I'm Daniel Sebastian, a postdoc at the University of Birmingham, and as I added to my title, I want to talk about what we can from binary stars, actually about the detection methods for exoplanet atmospheres. So what I'm talking about is first why we care about high-resolution spectroscopy, cross-correlation spectroscopy on binaries, and I'm talking about how we can measure CCF maps in the second, what effect of detrending do we see in our data. In the end, I'd like to wrap up with the potential for potential phase curves. Okay, let's go in. So cross-correlation maps we see in this conference very often, KVS maps. So just to summarize very quickly, so we use them to detect atomic molecular species by adding the signal which is buried into the noise. So since we're basically turning the planet star system in a double-lined system in this way. So we deriving the semi-amplitude of the planet can basically from the position of this blob that we see here, this very, very low signal detections, and we can, from the systemic velocity, what we measure here, we can actually infer some atmospheric dynamics. So we saw in this conference a lot about offsets, blue shifts. We have seen even double-lined peaks and so on. So one important part, if you look at this CCF maps, is basically how to measure this signal or the signal position. So if you look into literature about people doing it, it's basically typically fitting a Gaussian profile either to the CCF directly or in 1 or 2 dimensions, or to either to the likelihood map. So as we see in this conference and also in future, actually we are coming to more and more signal-dominated cross-correlation maps, and the question is, should we wait and do these Gaussians and 2-dimensional fitting, or should we maybe look into what kind of signal is in these maps? So this is the motivation for high-contrast binaries. So why we are using high-contrast binaries? First, we have the contrast ratios. If you take a solar-type star and an M dwarf, they are similar to a planet star contrast, 10 to minus 4, 10 to minus 5, and we know their atmospheres quite well because we know stellar absorption spectra, at least better than planet absorption spectra. So we can test these techniques on first on high signal to noise data, and second on existing instruments. And on the cherry on the top is we can create a benchmark FGK-M binary stars with this, where we can measure absolute dynamical masses. Okay, let me introduce one target that we are carrying off. This is TOI-1518. It's a solar-type star with an M dwarf eclipsing binary and has a very strong contrast ratio. The M dwarf is less than 0.2%. So it's a SB1, single line binary. So why we care about this target? First, it's the first circumbinary transiting exoplanet detected by TESS. And second, it hosts the first circumbinary planet only detected by radio velocities. So it's why it got the BBOP1 name as well. So you can see it's actually 2 circumbinary planets. And if we are going one step back to the binary, it's a question, can we use these more than 100 espresso spectra that we have been used to detect this outer circumbinary planet C to detect actually the M dwarf as well, and turning this to a double-line binary, measuring masses? And short question, yes, we can. So we do the classical high-resolution cross-correlation techniques, removing the primary lines using SVD, singular value decomposition, and cross-correlate our data or retrended data with a line mass and getting an 11 sigma detection, as you can see here in the KVS map from this M dwarf. If we are now interested in how we measure absolute dynamical masses with this, so we need to know where is this detection located. And you see it's not just a blob, so we have a signal at the expected semi-amplitude, but you see also this cross-like structure here, and you see these kind of side lobes that we see actually also in some exoplanet structures as well. So what we do is we not just do a two-dimensional Gaussian to it, but we build a model that we called sortier, and this is basically using the same method that we used to build this map at the first place. As you can see here, you can call it as you want, but basically you move the secondary or the M-dwarf in its rest frame, and if you're in the rest frame, you're summing up all the signal. If you are out of the rest frame, you get this kind of double-line structure, which is basically giving you this cross-like structure. So what we do is we take in one-dimensional profile, add it up in all the orbital phases. We have basically all the orbital phases covered of this binary, and repeat it for different semi-amplitude and create a map that looks like this, very similar to actually what we got. So the only free parameter from this model is the semi-amplitude, systemic velocity, and the 1D profile. So if you want, now you don't believe that a planet has a Gaussian, then you can change this profile. For instance, we used a Gaussian with some side lobes, because it's very well known for M-dwarf that you get some side lobes if you cross-correlate with a binary mask. Okay, so how does it work? So we see in our data, you can actually see it fits quite well. You see our our Gaussian with the side lobes, how it diminishes for higher semi-amplitude. And if you take this cut at a vertical cut here, you see this kind of structure and semi-amplitude is coming for free for our model, so there is no free parameter on this. So if you fit these kind of maps, you have to take a little bit of caution, because the noise in these maps is highly correlated. So you have to be careful with your uncertainties. But if you do it correctly, we're getting a 1% uncertainty of the mass for this M-dwarf, which basically turns it into a well-analyzed comparison system. So the question is, can we use this for exoplanet atmospheres? So yes, we can. So we used data from Project R 2012 and from Tao Bu, where CO detection has been made, and you can actually see how the sortier model fits quite nicely. You see the three star-like traces, so it's just coming from the three observing periods, and you see the data is actually fitting. And again, this is not a Gaussian, right? Okay, so especially these are very noisy data, more than 10 years old, so especially when we are going to more signal-dominated data, so I think it's very important to keep these structures into account. And if you like to use it for your upcoming ELT or upcoming observations, please use it. For our binaries, it's really, really useful. So you can go, it's a free open source code, and it's actually not an acronym. So in this case, it's actually inspired by the St. Andrews cross. And you can, so you can find it's basically a cross-like structures. We found the two horses here in the kelpies. Okay. This was the first thing that we learned. The second thing which we learned and that we're worried about, because we are using the SVD to remove our primary lines before we do the cross-correlation. So we know actually from the typical steps, like primary component, risk system fitting, whatever, always like we are doing something to our model data, so we are removing basically atmospheric signal. So the question is for our TOI-1518b, how much of the data is gone, and do we have any kind of orbital phase dependencies? So the second question actually we can answer by our data quite simple. We just measure with our sortier model data with different at different phases and see there's no change in CCF contrast. So we don't have orbital phase dependence, which is very good. So the second is how much is gone. So this is a little bit less easy, but what we can do is we know the absorption spectra of our star. So basically we can build a model and put the model with the same noise and the same SVD trending, and basically see when you compare this model without SVD and with SVD, there's basically nothing gone within the uncertainties what we get. So on the left side is the data, and the right side is the model. Okay. So this is quite good. So we are happy about this. We haven't lost too much of our data. So now we were a little bit worried, when actually do we get any effects of the detrending? Because this is what everybody is talking about. So and we looked in our models, what happens when we change more SVD components. Now this way well known, the more SVD components you remove, the more of your signal you remove as well. So you see here, this is our TOI-1518, so when you take 1338, oh my goodness. And you see that's what I just said, there's not much signal gone, and if you remove more components, you slowly start removing signal. And what is very important, what we found, is the signal of the atmosphere. When I'm talking signal of the atmosphere, is the signal to noise per resolution element in each spectrum. So I'm not talking about the cross correlation, I'm talking on the data. So that means what we find is that actually noisy data, like we have, are less than 1, are unaffected largely. And the moment you're getting to a signal to noise of 1 and higher, you're seeing strong effects from the degradation. So you get the degradation all over the orbital phase, and you're getting the phase dependency. So this is very important for more signal contained data, like for the ELT, to think about and to maybe solve it. Maybe SVD is not the right way, we will see. Okay, with this, I can now say we are well, because I have a signal to noise less than 0.1, so we can actually see the trace of our M12 for all the orbital phase, and we can actually present you a 220 ppm flat phase curve covering the full phase with high resolution cross correlation spectroscopy for this M12. And you actually can see it via different orders how the M12 appears towards the redder end, which is very showing that we have the M12 that directly detected. Okay, with this I come to my summary because my time is up, and we have two things that we learned from our binaries. First, we can measure CCF map easily using the sort time method, especially when we have application to very high signal to noise data. And second, SVD can keep atmospheric signals mostly unaffected if they are noisy. Thank you very much, and I'm taking a question.
speaker standing between you and lunch. But we've had an excellent session so far, so very much looking forward to our final speaker, Lorenzo Pino, who is going to tell us about, let's check. Okay, you're going to shine on.
Thanks, Jane. We're going to need that one later. I'm going to put it right there. Hello, everyone. I'm very happy that the last talk concluded with phase curves are possible from the ground at high resolution, because I completely agree. I'm going to talk to you about Shine On. It's an optical high-resolution phase curve survey of ultra-hot Jupiters that was made possible by the collaboration with many, many people listed over there. And I will not give an introduction to this crowd too long, just a reminder that, yeah, planets are 3D. We know that by now. And there are really a few key physical properties that we might be interested in. Dynamical properties, radiative properties like PT profiles, chemical abundances, clouds. So all of this, we don't just care about measuring on its own, but also about the interconnection between these kind of boxes that do not live. We heard this by Arjun nicely before. And we can specialize this discussion to ultra Jupiters, for instance, which are the target of this survey. We have effects such as cold trapping that remove maybe some of the strong optical absorption that could generate thermal inversions. We heard about that this week, and so forth and so on. Photochemical products generated in the day side might change and affect the chemistry even in the night side if they're circulated over there. So really, everything is interconnected. And I think this is a really strong motivation to go with high resolution from the ground, because it's the technique that can measure all of these three boxes simultaneously. With this motivation, we asked for a survey to target 16 ultra-hot Jupiters with 8-meter class facilities. It's a combination of espresso and of Maroon X. And this is the kind of region of the parameter space that we cover. So we have equilibrium temperatures in the ultra-hot Jupiter regime and planet surface gravities that vary, basically covering the whole parameter space. We went for, well, high-resolution spectroscopy. You know that by now. But we also went for broad phase coverage. We really wanted to do curvature to curvature whenever possible, have multiple epochs of observations at both sides of the eclipse when possible, because this is, I think, crucial to really manage to pin down the atmospheric processes simultaneously in these atmospheres. And yeah, the main objectives, as already mentioned, are to measure basically the thermal gradients, chemical abundances, and dynamics, all simultaneously. Now, a work in progress alert. This is for you here in this room, but it's especially for you at home who are watching at this talk while you are coding, having your cup of tea, and watching the stream of your favorite sport simultaneously. Look out for the questioning HoRSEs throughout the talk. They're gonna tell you how much more work is needed before this claim is made really solid. So have a look out for them. I'm going to talk about a couple, actually one target really, but in this room we have somewhere Adriano Micheli sitting, my PhD student, who will be very happy to talk to you about his preliminary results on WASP-121b. I didn't ask to him if he would be happy, but I'm sure he would be. I'm saying so. And instead I'm going to focus on Mascara 1b, another ultra-hot Jupiter. So here is the kind of data set that we acquired for this one. We have 3 pre-eclipse epochs with espresso and 1 post-eclipse epoch. We also have 2 more Maroon X epochs, which I still didn't look at. So this is going to be only a partial result on this target so far. I want to stress that Mascara 1b has had some high-resolution emission spectroscopy love recently. There have been a few papers that have detected species, that detected some hints of, detected thermal inversion and so far and so on. And I encourage you to check out those papers. And what I'm going to show you to you here is really some preliminary work in the sense that we forward model the atmosphere of the planet 1D, but we allow for some scaling using a set-consistent radiative convective model as chimera. We assume the circular orbit, and we used a likelihood approach to do all of this. Results. First thing, we can do precise exoplanet radial velocities, phase curves in other words. We can see the combined fit in black, that is the combination of the 4 nights that are color-coded, get to precision that are less than ½ kilometer per second globally, assuming a circular orbit. And it's also nice to see that the overall scaling of the models is consistent with 0 at 2 sigma. So that means, sorry, the logarithm of the scaling factor of the model is consistent with 0, which that means that basically our model successfully predicts the contrast of the lines compared to the background continuum. However, when we have a more detailed look at the posteriors of these distributions, you might see that there is something interesting going on. I think you can see my pointer. Yeah, especially when you compare the blue night, which is the post-eclipse, with the two pre-eclipse epochs that I'm showing here. In one dimension, they're fully consistent, but when you look at the corner plots, you might say that maybe you would want better agreement. And I think it's worth pointing out also that the orbital solution in the literature is slightly off. It's lying exactly on the post-eclipse solution, but the pre-eclipse are consistently shifted. So I think this is enough to start speculating a bit. The first thing we need to check, though, is that there is no boring effect that is creating a systematic that isn't accounted for, super important. So, for example, the ephemeris or the uncertainties in the orbital solutions. What I did so far is I forward modeled the, sorry, I had a double of that slide. I forward modeled the uncertainty on the KPV6 diagram basically by Monte Carlo Markov sampling, sampling within the uncertainty in the orbital solution, predicting the phases at the epochs that you are observing, so the uncertainty in the orbit of the planet, and trying to see what we will get from the fit. And our budget, estimated with this method, is around 0.5 kilometers per second, so that's quite significant, but I think it might still not be enough to fully explain this discrepancy. We will have to test further for that. Ultra-hot Jupiters are supposed to be circularized, but who knows? Maybe since this one particularly has a polar orbit, there might be some weird dynamical effect going on. So we had to check whether a possible, even small eccentricity can impact our KPV6 diagrams. In this case, we have a measured eccentricity that is really small from photometry, and this error budget is negligible compared to the other ones, so we're going to forget about that. Of course, my favorite explanation for this tension is that we have actually winds in the atmosphere of the planet. We will do this in a Bayesian way to test very carefully whether this is supported or not by the data. There are many people that now are doing phase curves from this. We will use standard methods, so nothing new there to explain. We'll see whether this holds up or not. I didn't show the green posteriors because they look slightly different compared to the other ones. And notice the 3 questioning horses here. Okay, but I'm gonna just show you the 4-point correlation plot now. The green posterior, if you check the scaling factor here, you can see that it's a bit smaller, and that is telling us, since we are doing full model reprocessing, that intrinsically the lines of the planet might be slightly weaker at this phase. And I'm going to point out here that this is the only epoch we have that is really pushing towards quadrature. So what if this is a dilution effect? With our correlation plot, we can see that indeed there seems to be maybe some kind of trend. We'll let the questioning horses take it in the future and see whether this holds up again after we do all our careful checks, but it's at least enticing. So the idea here would be that if you move towards quadrature, you see more of the night side maybe, so maybe less iron lines, because iron is what is driving these detections, after all, as in all ultra-hot Jupiters. Finally, I want to show you some very preliminary, as the night of yesterday, results on individual species detections. And despite the fact that these are very preliminary, I only put half a questioning horsey because, well, I think I'm going to take the hat now. Because despite the fact that we didn't look at the KPV6 plot, you might be hoping to see that, we did look at Bayesian evidences, which one could argue maybe is even better. We will do the KPV6 plots, don't worry, they're running right now. You can ask me at the end of the conference, maybe I will be able to show them to you. When we did this by looking at basically the full retrieval with a model that contains all species and excluding one by one and comparing basically whether one model is favored over the other. And well, iron, we have no doubt that this would be found in all 4 epochs. When we look at the other ones, we tested for some of them, like ionized iron, neutral titanium, TiO, magnesium-1, ionized calcium. And well, we see that we can exclude the presence of TiO. We do find evidence of Ti though, so I wouldn't claim any cold trapping so far. But we have to check, of course, the abundances. That is something that we will do after. I just want to mention still that when we combine all nights, we do get significant preference for models that indicate the presence of neutral and ionized iron, neutral titanium, neutral magnesium, and ionized calcium. So we only tested for a subset of the molecules we can and atoms so far, and we definitely will do more. Also, I want to mention that we definitely will look into the TIO line list to make sure that we're not excluding it on false premises. My conclusion slide says that Shine-On and similar surveys we have heard a lot about in these days definitely push the precisions on exoplanet phase curves down to less than 1 kilometer per second. We can definitely start gaining information on thermal abundances, thermal gradients, chemical abundances, dynamics, and we can potentially even refine the orbits of these planets with this precision. And in the future, I think it's really important to point out that we will definitely push towards analyzing towards quadrature, where I think very interesting dynamical and chemical hints might be hidden. It's more difficult because of the PCA removing the signal and all of that. Adriano is actually leading that effort in my team. And we're also moving towards developing more comprehensive, more physically rich modeling suites, including multidimensional chemical transport-based models with Vulkan 2D and cold trapping to try and explain simultaneously everything with better models. But while these are the conclusions, I'd just like to finish on a kind of a broader message. And again, I'm going to wear my hat for this one. Well, from Shine-On, we are moving towards a brighter, even brighter future. I'm thinking, for example, to the Andes spectrographs at the ELT. We made this plot for the white paper where we try to kind of hand-wavy predict how many planets will be able to do similar things that I've shown to you. This is in transmission, but the idea is, what if you take your prototypical hot Jupiter and you place it around a star with a magnitude of J equal 12? You get a 5 sigma detection above the red line. So 5 sigma detection is pretty good to do some chemical analysis and dynamical fingerprint. But I'm still going to put a questioning HoRSE here, because we really have a long way to do this very precisely. And I think it's also a great opportunity for us to sit down and come up, maybe in this conference, with an actionable bullet list of what we need to do to be ready before being able to actually make this true. Because, of course, we want to make the ELT the workhorse for exoplanets, right? But so far, this is still a dream on paper. And what I want us to do is for the 3 HoRSEs and 4 HoRSEs and 5 HoRSEs to make this a reality. And I thank you for that, and we'll take questions.
Welcome back, everyone. I'm Stéphane Pelletier. I'll be your chair for this session. And without further ado, our first speaker will be Luke Parker, who will talk to us about what happens when you go into the red.
Thank you very much. So, as we've already heard a few times this conference, the ELT is currently under construction in the Atacama Desert in Chile. And when it comes online, by the end of the decade, it will truly revolutionize the study of exoplanet atmospheres at high spectral resolution. And it will do this not just because it has a 39-meter primary mirror, but because it has a whole suite of instruments specifically designed with the study of exoplanet atmospheres in mind. At first light, these will be Harmony and Metis, shown here, and soon afterwards will be Andes. And we've heard a little bit about Harmony and Andes so far this conference, and the instrument that I've neglected here, which we'll hear about later, is Mikado. But in this talk, I'm going to focus on Metis. And the reason for this is that Metis has this unique wavelength coverage, the 3 to 5 micron L and M band spectral coverage. And this is a wavelength region we're really quite interested in, because, to start with, it has a huge number of biosignature spectral features. This is the Earth's atmosphere for R of 100, but of course we're not observing at R of 100, we get the full spectral features R of 100,000, so we can hope to do these really ambitious science cases where we look for biosignature molecules in the atmospheres of the nearest rocky exoplanets with Metis and the ELT. But if we want to do these really challenging science cases, we really need to understand the wavelength range we're looking at. And so far, no one's actually tested high-resolution spectroscopy at R of 100,000 for exoplanet atmospheres beyond 3.5 microns. And one of the reasons for this is there's a very large caloric contamination, shown here. But the key issue is that there is a very large sky thermal background noise. The Earth's atmosphere is hot and it is radiating at these wavelength ranges. So you can see this huge ramp beyond about 4 microns as the sky thermal background becomes a huge challenge. So we set out to see, can we use high-resolution spectroscopy techniques in these wavelength regions? And to do that, we use CRIRES Plus to look at beta pic B between 3.5 and 5.2 microns. And you can see up here in shaded regions the orders which we are sensitive to with these observations. Now, beta pic B is a directly imaged planet. So to study beta pic, we place down a slit on both the star and the planet. They're separated by about 0.2 arc seconds. And we disperse that light across the CRIRES Plus detector. This is a little bit of an indication of what a small section of the CRIRES Plus detector looks like in the M band. So you can see we've got very high background noise in the background. We have these bright sky emission lines shown here. And we have a lot of bad pixels, hot pixels, all sorts of normal instrumental effects. And I'm just going to walk you through very quickly some of the analysis that we do in the M band to get a planet signal out of this data. And highlighted in red as I go through here are elements of the reduction procedure that require substantial modification for use in the M band as opposed to shorter near-infrared wavelengths. So to start with, we do basic calibrations, the absolute requirement of AB nod subtraction. We clean out the stellar and telluric signals. And then to clean up these remaining residuals, we use PCA. So at this point, we expect random noise at all spatial positions, that's the y-axis in this plot, and at all wavelength ranges, with the exception of the planet position, where we expect this additional contribution from the planet signal buried in the noise. And to extract this signal, we of course use cross-correlation. So we expect in our high resolution, in our matrix to have the planet position localized entirely at the spatial position and at the orbital velocity of the planet beta pic B. So this is a very challenging wavelength range. What do we find? We find we can detect carbon monoxide at a signal noise of approximately 6.6. And this is really being driven from spectral features at 4.7 microns. You can see here, this is from order 2 of our detector primarily. We also detect water. This has been previously seen in the K band, but it's fantastic to be able to see this also in the L and the M bands. And when we look at these detections, they are certainly localized in separation and at the correct velocity, but they're also very broad. And these broad peaks come from the rotational broadening of the planet's spectral lines. So this is an indication of the rotation velocity of the planet, and we measure rotation velocities. These are blue and purple in the plot above, and we find these are consistent with previous studies in the K-band. But they do probe a higher pressure level, so this offers the prospect of using further infrared observations to probe different pressure regions in exoplanet atmospheres, and potentially with better instruments and smaller error bars, probe wind shear in the exoplanets of in the atmospheres of giant exoplanets. But these results so far are broadly consistent with what's been found in the K-band. So what do we get from the M-band that's a little bit more novel? And surprisingly, we see a signal from SiO, gaseous silicon monoxide. This is a tentative. It's a signal to noise of approximately 4, but it does seem to be well localized at the planet's spatial position and velocity shift. And we're really accessing this through the 4-micron band structure of SiO shown here. So SiO presents something of a puzzle, as previous observations of beta Pic B have suggested there are these huge magnesium silicate cloud decks on the planet where all the gaseous SiO would have condensed out into these cloud decks. So why are we seeing the SiO? We suggest 3 scenarios that could explain this. They may not be correct, but they're first working assumption. Maybe no magnesium silicate clouds where iron hazes are in fact providing those opacities seen at low resolution. Maybe patchy clouds where we're seeing SiO from lower in the atmosphere, or the clouds might be transparent at the M-band wavelengths we're observing. SiO is also exciting for these solid to gas accretion ratios. We've heard about this a little bit this week so far. And this is a way we can access the history of the planet formation at further infrared wavelengths. And as a final note, pushing towards smaller planets, SiO is one of those dominant atmospheric constituents of the ultra-hot lava worlds, which we're also very excited to study with future instruments. But let's take a step back. More data is required to confirm the signal before we speculate too hard on all of this condensation chemistry, formation, and future applications. Luckily, we have data that will do this. We have 7 hours more M-band data on beta Pic B, and there are other programs out there, particularly one from Marcus Janssen, who has 20 hours of mixed LNM band gratings. So more on this to follow, hopefully, in the near future. So this is what we can do with CRIRIS Plus in the M-band. What about METIS? So with CRIRIS Plus, we see that the main obstacle to detecting species is the thermal background noise. And as we go from our shortest wavelengths at 3.5 microns to our longest wavelengths at 5.2 microns, this is from purple to red in the plot above, we see that we drive this rising noise floor from the thermal background noise. So this is the main obstacle we currently face. But thermal background noise for these specific observations scales with the telescope primary mirror diameter to the power of 4. So going from 8.2 meters to 39 meters for the ELT, this is going to be a huge reduction for METIS. And we estimate for this particular science case, just by order of magnitude calculations, that this would be approximately 2% of the exposure time required with METIS versus CRIRIS Plus, and that's approximately 30 seconds of METIS time required to produce the results shown in this work with CRIRIS Plus. But of course, we need realistic simulations of all ELT instruments to assess their quality. So these are just simple scaling relations. In the final few minutes of my talk, I'm now going to switch gear completely and talk about a different project I'm working on, which is, are we equipped to observe transiting sub-Neptunes around M-dwarfs with existing instrumentation this time? And to do this, I'm using data from Hannah Diamond's program of GJ3090b, where we have 4 transits in the K-band with CRIRIS Plus. If you haven't heard of GJ3090b, this is described as one of the most favorable mini-Neptunes for atmospheric characterization, I think following only GJ1214b. And so this is around an M-star, and we see that the data we observe here in purple is composed of 2 contaminating signals, both the M-star stellar spectrum here in orange, which has a huge number of spectral lines across the K-band wavelengths we probe, and also the telluric spectrum. And we can see these signals in cross-correlation space. If we cross-correlate without doing adequate cleaning and produce a KPV sysmap, we can see signals from the tellurics and also the star. So these are very much influencing our spectra. But if we clean them, we find that we can effectively remove both the stellar and the telluric components, but we do not produce any detections from the planet. However, if we do a model injection test, we find that this data is actually incredibly sensitive to a large number of potential atmospheric scenarios. So this is telling us that we have some great constraining power on the atmospheric scenarios for GJ1390b. If we run a model injection grid, shown here, where we have the metallicity on the x-axis and the cloud deck pressure on the y-axis, we can show that we can rule out a large number of scenarios for this planet at lower metallicities and lower cloud deck pressures. Here is a model where we've injected the entire equilibrium chemistry with all the species into the data to represent the planet signal, and then we've only tried to cross-correlate methane out of it. Thank you. So the particular constraints we can get here are driven by the cloud deck, which truncates the spectral lines that we observe as you go to a higher and higher cloud deck, and also the metallicity, which shrinks the spectral features that we expect to observe due to the decreasing scale height. And finally, I just want to note that there are also JWST data coming for this planet. So we hope to be able to do complementary constraints from both the low resolution observations and the high resolution observations, which are particularly sensitive to this cloud deck pressure. And I'll leave you with my conclusions, and thank you very much.
Speaker will be Adam Langeveld, who will talk to us about the new kid on the block, Ghost.
This work? Yeah, great. So, 5,690 is a lot of exoplanets that we have discovered so far. But of these, only around 35 to 40, depending on your selection criteria, can be classed as an ultra-hot Jupiter. But in my opinion, these are some of the most fascinating objects that we can study for a variety of reasons. And judging by the previous talks at this conference, I don't really think I need to convince you of that either, or indeed why we are dedicating so much of our observing time to analyzing their atmospheres. We have already acquired a wealth of information about ultra-Jupiter atmospheres thanks to the power of high-resolution spectroscopy, particularly at optical wavelengths, where these atoms, metal atoms and ions are most prevalent. And here we can see some of the spectrographs, not all, that have been used over the past few years to do this kind of research, listed in kind of date order of their commissioning. And as of last year, 2 new HoRSEs joined the race, those being KPF at Keck and GHOST at Gemini South. And I don't really have too much time to go into KPF, but I would encourage you to seek out Alex Polanski's poster to talk to him about WASP-76. But for the remainder of this talk, I'm going to talk about GHOST, or the Gemini High-Resolution Optical Spectrograph, which is located in Chile at the Gemini South Telescope. It covers the entire, or most of the optical wavelength range up to the near-infrared around 1,000 nanometers. And the mode we're particularly interested in is this high-resolution mode, which allows for simultaneous observation of the sky with the target at a resolution of around 76,000. Just as a quick note, I'd like to mention and highlight a paper by Emily Diebert that we uploaded to arXiv yesterday, which was analyzing data during GHOST system verification run, and we analyzed or looked at WASP-121b for 3 hours during its post-eclipse phases. So if you're interested in any of those results, please seek out Emily's paper, or we can chat afterwards as well. But for now, I'm going to talk to you about the first results from transmission spectroscopy with GHOST. Here we have, I've shown all of the ultra-hot Jupiters that we know of and their parameters, and during GHOST's shared risk run following its commissioning, we decided to observe HAT P70b, which is a particularly interesting ultra-Jupiter, given that it's one of the most inflated that we know of, with a radius of around 1.8, 1.9 RJ, and a temperature well into the ultra-hot Jupiter regime, close to around 2,500 Kelvin. Now, this planet has been observed before with HARPS North, with Aaron's paper, and they detected several species in its atmosphere, and so we expect these to be in our GHOST data as well, plus more given the increased signal to noise provided by Gemini South. I'm going to skip over most of the analysis and reduction processes, since by now we're all familiar with those. But the one thing I do want to mention is that for these data, I used MolecuFit for the telluric corrections, and spent quite a lot of time kind of integrating the GHOST data within MolecuFit and writing some code to extract the relevant information. And I do plan to make this publicly available for your help soon, but if you're interested in using GHOST before that time, then feel free to reach out and contact me if you want to save some time with that. The one thing to just take away from this plot is this orange line here, which is the final spectrum that we work with, this telluric corrected spectrum. So going through the standard techniques to extract our transmission spectrum, I'm going to skip straight ahead to the transit residuals, basically phase versus wavelength, and showing here just a region around the ionized calcium triplet. And we can see here that there's clear evidence of the planetary absorption, which follows the diagonal path that expected, as we're all familiar with. And what's quite nice about this is that it clearly shows that GHOST can do this for singly resolved lines. In addition to this, we see these bright features going in the opposite direction for HAT P70, and that is the spurious feature from the Voss-McLaughlin effect. And in order to do this, we kind of ideally want to use a model, which we're currently working on. So for now, I'm just going to simply mask out the data and proceed with the analysis. If we combine all of the data now between the C1 and C4 transit points in the planetary rest frame, we can extract a high signal-to-noise combined transmission spectrum, which looks something like this, and we can see clear evidence of the calcium absorption in its transmission spectrum. And there's a few things we can note from this. Firstly, if we fit Gaussians to the line profiles, we can measure the peak position. And I'm not sure if you can really see here, but I will tell you that each peak is blue shifted by a few kilometers per second, which is consistent with other measurements from other ultra-hot Jupiters and hot Jupiters as well. In addition to this, we can measure the line depths of these lines. For example, if we take the strongest line in the middle of the calcium triplet, around 1.25%, we can translate that to an atmospheric height of around 50% times the white light planetary radius, which means that if we are observing at this specific wavelength, we will see the planet appear 50% bigger than it otherwise would be in the integrated white light. And so really with these strong and single line species that we can see in these transmission spectra, we are really probing the upper altitudes of these ultra-hot Jupiters to understand what's going on at the very extremity. Following this, I applied the standard cross-correlation techniques to try to find other chemical species in its atmosphere. And we detected an array of species, but just as an example, I'm going to show 6 here. And the first 4 on the left, I'm going to call these strong phase resolve detections. And by that, I mean we have these strong planetary absorption features that are clearly visible across the entire transit, and where we take each row of these CCFs, and we can analyze how the signal changes through time and through the orbit. And so we really get an idea about the 3D nature of the atmosphere as it rotates through the orbit. On the right-hand side, I'm just showing an example of 2 of the weaker species where we can still see some evidence of the planetary trail, but the phase-resolved aspect is a bit more tenuous. But perhaps we can still do that by kind of combining the first half and comparing it to the second half. So just the key point, again, that I want to mention here is that with GHOST, we have shown that we can clearly do these phase-resolved detections in order to analyze the 3D nature of these atmospheres. Now going forward, again, I'm just going to mask out the RM effect for now, and we are working on a model to do this so that we can look at the in-transit phases. But producing the KP-VSIS maps that we're all familiar with looks something like this. And we can clearly see that each of these species shown here, and more that we have found as well, shows clear evidence of absorption in the atmosphere. And from these peaks in these CCF maps, we can tell a few things. Firstly, if we look at the radial velocity value of these peaks, we can see that all of them, even the ones I've not shown, were blue shifted from 0, because we're now in the planetary rest frame. And this is, again, indicative of this day-side to night-side atmospheric flow slash winds that we are all kind of looking at now with these kind of detections. On the other axes, we see a variation in KP for each of the detected species. Now, I will caution here that the error bar on this is quite large, but it is not to be unexpected. It can be expected. For example, last year, there was a study on Kelt 9b, and 18 species were identified covering a range of orbital velocities of around 60 kilometers per second. And so we are really seeing that with our HAP-P70b data as well. Some similar effects are occurring here, and potentially we are now probing different layers or regions of the atmosphere, thereby also investigating this 3-dimensional properties and processes. So with that, I kind of just want to finish by quickly saying that our understanding of ultra-hot Jupiter atmospheres has really flourished over the last 5 to 6 years, thanks to the power of high-resolution spectroscopy. But with all of this information, what is next? What is lined up for the future? Well, at this point, I am very happy to introduce to you the Spectra Ghost survey on Gemini South, which is a new large and long program which we are running next semester, led by myself and my collaborator, Emily Debert, and the following people listed at the bottom here, many of whom are at HoRSEs today. With Spectra Ghosts, we aim to investigate and use GHOST to look at a sample of 10 ultra-hot Jupiter atmospheres to perform a detailed and homogeneous analysis of their atmospheres, both in by analyzing its terminator in transmission and also its pre- and post-eclipse day-sides with emission spectroscopy. And just as a kind of a teaser of what's to come, the first 2 planets that I showed in this talk are also included in our Spectra Ghost sample. And so you can begin to understand what kind of detections and what information we will be able to learn from their atmospheres. And hopefully I'll have an update for you on this at 3 HoRSEs, whenever that may be. So to wrap up this whole talk into one kind of final overarching summary and bring back this figure that I showed earlier. In the early 2030s, the Andes spectrograph will be built for the ELT. And as demonstrated by the complete contrast to anything else in this figure, it is set to revolutionize our understanding of these kind of atmospheres, given that the ELT itself will collect 15 times more light than the current state of the art. And so you can only imagine what we will be able to do with just a single transit of, say, an ultra-hot Jupiter with Andes and the ELT. And this was very nicely summarized by Jens in the first talk of this conference, where for particularly the most visible targets, the brightest targets, we perhaps won't even need to rely on the cross-correlation technique anymore to look at these individual lines of these species. Therefore, in order to kind of exploit the full potential of Andes and the ELT, I think it's kind of imperative that we continue to do our best, meanwhile, to investigate what we can to understand the three-dimensional nature of the atmospheres and kind of bring together these theoretical models that were very well presented by Haley Beltz a couple of days ago to try to describe some of these weird and wonderful features that we see in their transmission and emission spectra. So I would encourage us all to keep spending our observing time and resources to investigate that. So while we currently think we know a lot about ultra-hot Jupiters, I would really argue that we are just beginning to scratch the surface on our quest to understand their exotic nature. Thank you, and I'll be happy to take any questions.
Questions?
our next speaker, and I practice for this, will be Lennart van Sluijs. Yes. Who will tell us about how WASP-189 looks once you've had a bit of red wine.
Great job on pronouncing my last name, so I actually won't have to do it again. But I'm Lennart van Sluijs, and I'm a postdoc currently at the University of Michigan. And I'm really excited to tell you all about wine reds. So I will share a first view of WASP-189b with wine red. Wine red is actually a new near-infrared spectrograph on Magellan. So the first thing I asked the AI DALL-E 3 to actually give a first view of this planet, with 2 horses enjoying that view. I especially love this image because it added the 2 straws, because of course it's a bit inconvenient if you have hooves to sip your wine from a glass. Okay. Moving on, so just very briefly, what's the science motivation? What do we want to do as a community? We want very precise abundance measurements for a whole wide range of elements. Why do we want to do this? We think we can constrain planet formation pathways, as we've seen before already in a couple of talks. So we have, for example, this idea of snow lines, that maybe it's related to the C/O ratio. This idea that maybe the refractory to volatile ratio, which we can measure for the ultra Jupiters, is related to the rock to ice ratio, which also links back to the planet formation location. Also this idea that we can link it to the dynamics. So the chemistry and the dynamics, planets are really 3D. So there's, for example, this recent paper by Sid Gandhi, where this is more about the chemistry, but that you see that what bulk abundance for water you retrieve depends on the water dissociation model that you use or not. And also we've seen this idea of maybe cold trapping, where certain refractory species are probably condensed out of the atmosphere. So in order to do these measurements, we of course need instruments. So I want to introduce you to wine red, which is a high throughput, high resolution spectrograph between the optical and the near infrared. And this is the outside, which is painted wine red. So wine red has an excellent throughput of about 40% and a resolution of about 68,000, covering the Y and J bands. Simultaneously is at a slightly lower resolution, yeah, it can either do the Y or the J band. So if we compare this to other spectrographs in the field, I'm sorry if your favorite one isn't in this plot, but we can see on the x-axis spectral resolution and on the y-axis throughput, and we can see wine red is like really, really high up there, which is achieved through a very high inclination angle. So the shell order is very high. Then it comes a bit at the cost. So the coverage of this instrument is shorter, for example, than something like IGRINS. But yeah, still pretty high up there. For example, comparable to Cryo-S+. So why do we care about the Y or the J band? Well, the Y band, there's actually one publication now on a non-detection on an ultra-hot Neptune for the helium line. But I've heard some more optimistic things from that consortium, so I guess there will be more to come there. But this is not what I do. Today I want to talk about the J bands. And the J bands, we have, for example, OH, CO, and water, although there's better, admittedly, for example, if you go towards the further near infrared. But this helps, for example, with C/O ratios or water dissociation. But very crucially, very interestingly, in these bands, we have TIO and VO, and they peak there, or they peak in the optical, but of course, in sort of in between these two wavelengths, you actually also benefit from that your planet-to-star ratio is still more favorable towards the planets compared to the optical. And also, we can have things like iron, probably a whole range of other refractories that I'm missing here, from what I heard during this week. and also iron hydride, so FeH. So there's a whole range of molecules that could help us understand these processes better. So these are all of them. Well, it was a lot of fun. I got to observe actually at Las Campanas Observatory. It was a very hands-on instrument. You actually press the button to take exposures. It's a 6.5 meter telescope, so quite big. There's also horses sometimes in real life. Yeah, I've seen horses there. So what's the current state of the survey? These are, we see equilibrium temperature on the x-axis, on the y-axis, the gravity of the planet. So we have 5 targets. At the moment, most of them have been observed in emission. So we have some post and pre-eclipse data, and also some night side pre-transit data for WASP-121b. So ideally, at some point, when this is all up and running, the bigger goal is maybe to look at things like 3D-ness. So, for example, I've been looking at this with WASP-33b, where I sort of look at a CO detection, and I see that it varies during the transit. So, but we need post and pre-eclipse data to do that. There's also really good synergy with, for example, the IGRINS program. We have great collaborations there, so I think we should really use this so that we get an even broader wavelength coverage. Today, I want to focus on WASP-189b, which has been observed again in emission in the J-band. So we have 2 nights of observations. This is a very preliminary result still. It is actually really hard to work with a new instrument. There's a lot of processing to do and seeing what's sort of the best observing strategy. So I used the warp pipeline, which was provided by the instrument team, which extracts the spectra from the shell frames. But you can see from these frames, there's a lot of cosmic rays and reflections and a lot of complications. But I managed to extract the spectral time series. And the really good news is that we're achieving the expected signal-to-noise ratios with this instrument, so that's good. I then used a modified version of the IGRINS data reduction pipeline to remove some bad frames, normalize spectra, align them, as we've seen before, and also PCA. So what are the preliminary results? Unfortunately, or maybe as expected, I'll come back to that, I don't see any water, TAO, VO. There's, I think the most tentative signal I'm seeing at the moment is iron, but it's quite offset. But I think the iron should really be there, and I'm convinced more of that seeing previous talks during this conference. So for this, I used chemical abundances from a paper by Bibiana Prinot, and also a PT profile for this planet, but maybe there's now better profiles out there. It also seems to be that mainly post-eclipse we're seeing sort of a signal when we do this in cross-correlation space. So I'm really investigating the signal in more detail, so more to come there. But if we take this sort of as it is, these non-detections, can we understand it? Well, actually, this is a really hot planet, so maybe the TAO and VO are simply dissociated. And this is also maybe somewhat in line with the fact that TAO has not been detected with other instruments, although we have seen titanium on its own has been detected. But in this plot, again by Bibiana, you can see that the dissociation is happening quite quickly for TAO. So this is assuming equilibrium chemistry. Then also water dissociation. In IGRINS, we have stronger water opacity, so maybe that's why we're seeing a weak detection there. We haven't seen it, I think, with Cryo-S Plus. Maybe also as expecting. The iron is puzzling, but again, there might be a tentative signal there, which I'm currently looking into. I think the main thing I'm checking at the moment is the stability of the wavelength. So I'm pretty sure the wavelength solution is okay by sort of comparing a telluric model to observed spectra. But the stability is really key to make HiRES a success. So that's what I'm currently investigating. So work in progress still. To take home, well, there's sort of 2 horse states. You have this proposal, you go observing, and then you look at the real data. But as you interpret it, maybe you'll feel more confident again and get back to the first one. Anyway, to take home, really, I had a first look at WASP-189 with wine rats. There's a bunch of molecules that are sort of niche in between the optical and the near-infrared that can constrain these cold trap mechanisms, water dissociation. Wine rat covers those bandwidths, has a very high throughput, and there's some preliminary results that I show that are kind of in line with it being with this very hot planet having very hot day sites. But there's definitely more to come. I'm very excited, especially to get more data on the cooler targets, where I think maybe TAO and VO should be more abundant. So definitely more to come from this survey. Thank you very much.
Our next speaker will be Maddalena Bugatti, who will speak to us about yet another instrument named after a beverage, ristretto. Oh. Take it away.
Okay. Hello, everybody. I'm Maddalena, a PhD student at the University of Geneva, and today I will talk about the ristretto simulator to simulate exoplanet reflection spectra. For those who do not know, because not everyone knows, ristretto is a coffee in Italy. It's half of the size of an espresso. It's not only a coffee, it's an instrument that is being built at the University of Geneva. It will be installed at the VLT, 8 meters telescope. It includes an extreme adaptive optics system and an integral field unit of 7 single mode fibers. And a spectrograph, of course, you're here for spectrographs. It's in particular an shell spectrograph. So let's focus on these last two things. For those who are not familiar with IFU, you can consider to look at a target in the sky and divide the sky in different regions. Ristretto divides the sky in 7 hexagonal regions and is able to extract a single spectrum for every one of these regions, which is very useful because you can really separate regions in the sky and obtain spectra of them. The distance of these pixels projected in the sky is about lambda over d, so we are really pushing the instrument at the diffraction limit at the VLT. It's about 40 milliarc seconds. So Ristretto has a high spatial resolution. Then the spectrograph itself, the range of the wavelength is between 620 to 840 nanometers, and the resolution is 140,000. So Ristretto has also a high resolution spectroscopy. These two things are combined together, are very powerful. This is an image of Io and Europa, the moons of Jupiter, and Ristretto projected on them. You can see that we would be able to literally scan the surface of these two objects. We have these two powerful spatial resolution and resolution spectroscopy that are very high. So they together make the perfect coffee. The goal of Ristretto is to study the reflected light of exoplanets. My goal is to simulate in advance the reflected spectra of Proxima b, seen by Ristretto. Let's see the system itself. Proxima Centauri is at a distance of 1.3 parsecond. It's smaller and lighter than the Sun. The planet has a minimum mass of around 1 Earth masses, and it's very close to its star, and it is very fast, let's say, so it has an orbital period of 11 days. The distance on the sky at the maximum elongation is exactly 40 milliarc seconds, so the distance between two pixels seen by Ristretto. This is to tell you that Ristretto is literally the perfect instrument to study this system. Challenges for this: it is a faint planet, it's a temperate rocky planet. We assume a flux ratio of 10 to the power of -7, and there are problems linked with the instrument itself, of course, like in every instrument. The PSF and the coupling of the fibers that actually cause the spectra that vary in each fiber, and this variation is wavelength dependent. We cannot prevent it, it's like an instrument limit. My simulations started with the simulation of the synthetic input spectra, star's halo, and the planet itself with the correct radial velocities components, so barycentric, systemic, and orbital. Then I simulated also the fiber coupling, so I applied these variations to my spectra. I used a Python package which is called PyShell to generate 2D shell spectra, which includes actually the PSF and the noises of the instrument. And then I hunt my planet, so I search Proxima b in the data. To simulate synthetic input spectra, for the star, I used a Phoenix model with an effective temperature of 3000. And for the planet, I used a 3D global climate model considering an Earth-like atmosphere. Here are represented the two spectra of star and planet. As you can see, they are very similar because we are studying the reflected light. So we just have some extra absorption lines in the planet spectrum, which are due mainly to water vapor and oxygen in this wavelength range. Then the fiber coupling. Here you can see a map in the sky of the efficiency of the 7 fibers or spaxels. We plan to put the star in the central spaxel and then observe the planet around. So I assumed some orbital parameters that we do not know so far, like the orbital inclination of the planet. I assumed it to be 60 degrees, and the angle, let's say seen on sky, I assumed it to be 0. And here you can see the projection of the orbit of the planet around the star, seen on the sky. I assumed an observations frequency every 11 days to be sure that the planet is at its maximum elongation. It's possible also to observe it every 5.5 days, let's say, so when it's at the two extremes. And I assumed a total observing time of 100 hours spread over 3 months during the winter in Chile. PyShell, so again, it's a Python package to simulate HL2D spectra. Once we give PyShell some synthetic input spectra, PyShell can add telluric lines depending on the position on Earth and the day of observation. Then it uses the optical model of the spectrograph itself, which is given through some matrices, to simulate really the way of a photon inside the optical elements of the spectrograph. And so it recreates also the PSF. It adds some bias and readout noise, and then it creates this raw frame, which is commonly what we see for shell spectrographs. Okay, so how did I do my analysis once I simulated all this? I assumed two exposures, one long one where I put the planet in an off-axis pixel, and one short one with the star in an off-axis pixel. I assumed 1 hour exposure maximum, so 100 total exposures. Then I apply radial velocity, noises, whatever you want inside. It's created the 2D raw frame. I extract the 1D spectrum using a technique which is nowadays used for shell spectrographs, which is called optimal extraction. Here you can see it's normalized flux, so be careful, they look exactly the same, but it's normalized flux. The one at the top includes the stars, halo, and the planet. You can see the logo of the planet. And the bottom one, just the star. And then I model the and then I want to correct the spectra. I want to correct them from the variation due to the coupling PSF and whatever you can think about due to the instruments. So I pass the spectra through a low-pass filter. In my case, I used a Gaussian convolution. And I normalized the spectra to remove these low frequencies that induce spectral variations. Finally, I perform a fit. So I model my spectra of axis, which includes, again, star, halo, and planet, as the star only, times a certain factor alpha, plus a rescaled factor, and times the Doppler shifted star. So it's literally star plus shifted rescaled down star, which is shown here. Thanks to this model, I do not know in advance any assumption on the atmosphere of the planet other than the flux ratio is 10 to the minus 7. This is because I try to perform CCF and other methods, but these flux variations that people don't take into account, it's really a mess, and it prevents me to completely remove the star signal from the spectra where there is also from the spectrum where there is also the planet. So resume and preliminary results. I considered exposure time of 100 hours, flux ratio between planet and the star of 10 to the minus 7. As model for my fit, I consider star plus shifted star scale down. And as free parameters, I consider the orbital inclination of the planet that actually tells me afterwards what is the radial velocity of the planet at every single exposure, and the scaling factor. This is an image that I computed without counting the telluric lines and the PSF. So there are noises, there are the coupling functions, etc., but I do not obtain such a beautiful image still if I include telluric lines and PSF. So as you can see, this is the chi-square plot. I put at the beginning an inclination of 60 degrees. We can see a hole at 60 degrees, so we can say, okay, we detected something, and we can constrain actually the orbital inclination of it. And if we consider an inclination of the orbit of 0 degree, is exactly as saying there is no planet in my spectrum. As you can see, the chi-square jumps up, and this difference can tell us statistically, okay, then I have like robust detection of my planet. Okay, perspectives for the future. I want to implement a chi-square study into PyShell. By this, I mean including the PSF and the telluric lines that are not still, I don't have still very good results. I see something, but it's not very good. Develop a robust statistical strategy to validate the detectability of the planet and its parameters, because we can, for example, do some nested sampling or consider the Bayesian information criterion or some statistical, let's say, robust methods in order to say we detect the planet with this strength. Then complexifying the planet atmosphere composition and justify that the fit that I do is actually better, because if you add a free parameter, for sure you have a better fit. I mean, you can add 1 million parameters and you'll have a better fit, but it doesn't mean that actually it makes sense statistically. And finally, apply the simulations on other exoplanets. Thank you very much. This is the team of Ristretto. It will be ready in 2028. There is a site and some papers in the archives soon. So yeah, thanks.
Bifani, who will talk to us about Mikado, a first light instrument for the upcoming ELT.
Okay, hi everyone. So I'm gonna talk to you now about Mikado. I am Paulina, I'm on my last year of the PhD. And just to put it a bit into context, I'm usually an observer. So I mostly use VLT data, so this kind of mirror. And I have characterized the atmospheres of different directly imaged companions. So for instance, AB peak and IF-Lab. They're very different companions. And as an observer, we want more data all the time. And this brings us to think about the next generation of instruments. So the next generation is going to be the ELT. So this, of course, is not ready. It actually looks like this now, as you have seen before during today. And as you may know, there's going to be like several instruments that are designed for this. And the ones that will actually be tackling the exoplanet science case are Mikado, that comes with Morpheo, that's the AO module. Then we have Metis, Harmony, Andes, and at the end, like PCS. So here I ordered them by the time where we have the first light of the instrument. And so from the previous talk, this session, actually Mikado was missing there. Mikado is gonna be probably there first. But what is Mikado? So Mikado is actually a multi-AO imaging camera for deep observations. So it's not designed to be a spectrograph. It's not designed for high resolution. And it's, in terms of HoRSEs, about 3 horses height. So actually like a small house. And it's a general purpose instrument. It's not specifically designed for exoplanet science. It's gonna be toggling all these different science cases, trying to get like the best images, like deep observations out there. And exoplanets are just one more science case. And as I was saying, it's an imager. So how does this look in terms of the Beta Pictoris system? So here we have a sphere image of Beta Pictoris. So we can see here the debris disk and planet B just right there in the middle. But with the sphere observations, we cannot see planet C that was actually discovered by radial velocity and gravity observations after the sphere images. But it's just like they're under the coronagraphs, so we cannot see it. But as Elsa and Pierre Boudos, as part of the Mikado and Morpheo consortia, which are like my supervisors in this project, showed, if you run like 1 hour ADI sequence with Mikado, you actually can get this kind of observations. So planet C here pops out nicely. Just like the coronagraph here is way smaller. Like our resolution, like spatial resolution here is incredibly like to compare to sphere. But we are here to talk about high resolution, not imaging, right? So in terms of timeline again, this is like the schedule for the different ELT instruments. And in terms of spectroscopy, as Arthur Wiegand was saying early this week, we have Metis. So Metis is gonna be one of the first like instrument. So actually, which one will come first, we don't really know. But for high resolution like goals, actually they are very complementary. Metis will be here. Mikado is gonna just probe the other wavelengths. And then we will have Andes that will just like probably will be much better in Mikado for high resolution spectroscopy. I'm not gonna discuss that, but we will have a 3 years gap in between. So we can use the spectrograph of Mikado during these 3 years before Andes arrives. So Mikado will have actually 3 options for the slit. So it's gonna be a slit. There is several conditions because there is not gonna be air dispersion corrector, so the slit must stay aligned with the parallactic angle, which like makes a lot of further problems for data reduction. However, we will have, for instance, H and K bands simultaneously, or Y and J bands simultaneously. And if we look at the H and K band simultaneously, what will happen is that the slit will project the spectra, like we will like disperse the light, and the spectra will be projected over the detector, which actually is separated into 9 different pieces, so there will be gaps and stuff, but again, the consortia is dealing with this kind of stuff, so there is gonna be this nice package that's being developed, ScopeSim, that's gonna deal with like all the instrumental effects and the processing of this. But for exoplanet science case and for directly imaged exoplanets, actually we are like limited by the fact that we're trying to observe these very, very faint sources right next to like bright stars. And when we want to use the slit, we won't have a coronagraph. So actually here, this is a planet, all the rest of this is the PSF of the star. So how actually, like the questions here is, how close can we get, like how close can I put here the planet in order to detect it, and how like much in contrast can we actually achieve to, so the main question is which are gonna be our best targets, and like what's the interesting science we can do with this. So in order to answer these kind of questions, we are running end-to-end simulations. What does this mean is we're trying to develop a framework to create data, then reduce our data and extract the planetary signal, and then analyze which will be the capabilities of Mikado. For this, I'm just gonna quickly go through this. So for the data construction, we're using, so I'm just gonna show here. So we're using Mystic PSF. So Mystic is a code, it's a like private code, but if you're ever interested, you can ask me. So this is developed by Pierre and Elsa in Paris. And what will happen is that we can create very realistic PSF cubes for the ELT. So all this is because of the spiders, and then you see that the wavelength actually makes like your speckle increase in size. So we are taking atmospheric turbulence into account and a bunch of other effects. And then we want to put a slit over this. So I put here a slit for the star and a slit for the planet, because I have both objects will have like the same PSF function. So in terms of how this slit will look, it's gonna be something like this. So the slit for the star is rotating. The slit for the planet is aligned on the center of the PSF. Why do we do this? Because we want to observe the planet. We want to observe known planets. So actually we can lock the AO system to follow the planet, but the speckles of the star will be just like crossing through at different wavelengths at different times. So this axis here is time. Then we multiply each stellar and planetary PSF contribution by their spectra at 20,000 resolution. So we are using this model, so we can vary the planet spectra and the star spectra. And we just add both contributions, and we get this kind of data. So slit length, time, wavelength. So these are cubes that are like have these 3 dimensions. We're putting it like this because what you can then see here is that this arc is actually the planet. All the rest is the star contribution. And if we just wanted to extract the planetary spectra out of this, so we could follow the trace, but it looks like this, okay? So what's happening is that different speckles of the star, because they're moving with wavelength, they're gonna cross our slit at different times, and this will create like this kind of wiggles where we will lose our like planetary signal. So for this then, we are developing the next step, the data reduction process. So there are several ways of doing this. We are trying this approach of doing kind of a spectral deconvolution. We could argue to try to test other stuff too. But basically what we do is we have our like, we call it STS, so slit temporal scanned area. Then we apply, like, we need to apply a filter to like smooth the edges. Then we apply a Fourier transformation to like change the pixel scale so that now our speckles have the same size at all wavelengths. With that, we can create a stellar model of the speckles, multiply that by a stellar spectrum, subtract it, and then get this kind of thing. So the planet signal then will pop out there. Then we go back to our original pixel scale, and we could be able to recover a planetary signal. However, this is like, we're still optimizing all this algorithm. You can expect it to be out in about early 2025. And what will happen then is that, well, we have our like original spectra, and then we recover something that looks way more similar to what we expect for our planetary spectra. And what do we want to do with this? So I'm not, like, I've tried to characterize individual systems as HR8799E, individual planets. However, what we want to answer is which kind of planets at which kind of contrast and separations we could able to, like, we would be able to access, and quantify the atmospheric characterization capabilities in terms of other instruments and synergies out there. So this is just like more ideas right now. We're still like developing the second part. So in terms of contrast and separation and contrast, we're having like this kind of plots. So the fact that the PSF has this shape and we're trying to get like as close as possible will mean that at some angles we will observe better or not. So we're trying to answer actually, is this important for our case? Like for different cases. And then we are like, I'm the co-developing Formosa, as was presented early this week by Alan and Matthew. And with Formosa, we will have this kind of code ready to actually use this high resolution data and model it and extract atmospheric parameters. And then, yeah, we will try to see how Mikado actually will help us to go further in terms of characterization. So the ELT looks like this. My project is still under development too, but we still have a bunch of time because Mikado will not be there for another like 5 years or so. But the main takeaways that I want you to stay with is the ELT will be a characterization machine. We will not like discover new planets. It's not like the goal. So this kind of instruments and this kind of modes, the spectroscopic mode of Mikado, are meant to be used for characterization. So we need to tackle like known exoplanets. It's gonna be one of the first instruments, so you don't want to forget about Mikado. And something that's really like not being explored at all by the different consortia, so by Mikado and Morpheo, is transiting hot Jupiters. So we may want to explore this in the future. If you're interested, you can talk to me about this. So thank you.
Welcome back to our final session of the day. And our first speaker will be Katja Poppenhäger, who will talk to us about Andes.
Close enough to the mic, is this okay? Yeah, very good, okay. Yes, hello. Today I'm mainly talking about instrumentation stuff, but I think most of you know me as an observer. I am still an observer. So why I'm talking about Andes is because I have the wonderful privilege to be working with a lot of people at the AIP Potsdam, so down the road from here, who are engineers and instrumentation people and who are working very hard to make Andes become a reality. We had a couple of white papers out last year from the Andes science team, and I'm going to present some highlights from the Exoplanet working group. And also I have stuck a little bit of my own science towards the end of the talk because I didn't want to go completely without talking to you about my own science. So, Andes, you have heard about Andes a number of times already during this conference. A few key points about Andes. So, we're talking about the second generation instrument at the extremely large telescope, high resolution spectrograph with a resolution of about 100,000. We have a broad wavelength coverage from, and you will see this a lot, there's like a nominal baseline design and a goal. So we have a wavelength range that goes, actually there's a typo there, it's 0.4 to 1.8 microns, with a goal to extend that both in the near UV and towards the K-band. It has two observing modes that we're going to talk about in just a little while, a little bit more. One is a standard seeing limited spectrograph over the full wavelength range, and the other one is an AO assistant mode that you only use in the infrared, in the near-infrared range. Now, we are currently in the ESO phase B in the preliminary design. We're scheduled for first light, hopefully not too far from now. We're looking very much forward to that. And I'm going to talk a little bit about what we have here. So this is one of those typical diagrams that we see a lot in our consortium. And what you can see here, I'm going to do this with the cursor so I don't have to move away from the microphone, is basically the spectroscopic subsystems that you're seeing here, yeah, these four things. My team in Potsdam is working on the UBV subsystem of Andes, and you see also here the RIZ and so on and so forth, going towards the longer wavelengths. Now, for Andes, it has a bunch of high-level science goals that drive the design of that instrument, and two of those particularly important science goals have to do with exoplanet studies, namely studying them in transmission and reflected light. And ideally, of course, we want to push towards the small planets in the habitable zones around their host stars. We have talked a lot about seeing limited transmission and emission spectroscopy, so the standard thing that many of us have been doing. And also during this conference, we heard already about quite a number of interesting designs and instruments that work with this high spatial resolution plus high spectral resolution mode to improve the contrast of your planet to star. For Andes, this is what this will typically look like, these two observing modes that we're going to have. The top is the CM limited one, where you basically have your PSF there. It gets on a single large fiber, then we have a fiber-to-fiber interface, and what you see here is basically then it gets put on a fiber bundle, and then it gets distributed like this along the slit of the spectrograph. The other mode that we hope will very much do for us for the reflected light science case is the IFU AO-assisted observing mode. We basically have, and we have seen this earlier today actually as well, where we have here various fibers, and let's say your planet is here, you can improve the contrast of your reflected light from the planet to the residual light from the star that you have there, and then you basically feed the light from those fibers in a certain order into your spectrograph so that you can separate those spectra from the various spaxels. So, I talked a little bit about white papers already. We had a bunch of interesting things that the whole science team, in particular the Exoplanet working group of Andes, has worked on over the past year. So there's a whole bunch of simulations that many of my wonderful colleagues at other institutes did. It's a large collaboration. For transmission spectroscopy, when we try to target the outgassed atmospheres for small planets in the habitable zone, for example, for the TRAPPIST-1 planets, we find actually when we simulate such observations for Andes that those atmospheres are detectable within a relatively
decent number of stacked transits. So we have here for TRAPPIST-1D a very significant detection of such an atmosphere as modeled in 5 transits. So that's definitely in the feasible realm with the ELT. And I should also mention, if you want to look this up in detail, the science paper, the white paper has much more than I can cover here. So this is the paper led by Enric Palais, and you can find it easily on arXiv. Also for the transmission spectra, if we go away from the habitable zone, but go towards the warmer, small planets, or, which you see on the other side here, the more Neptunic planets, then we actually find that there is a pretty good sample of already known planets where we can characterize their atmospheres for this side here in about 5 transits and significantly detect their atmospheres either for CO2-dominated ones or nitrogen-dominated ones. And for practically the whole population of known Neptunic planets, we can characterize their atmospheres in a single transit with Andes. Now, coming to the reflected light science case, as we have seen today and also over the rest of the conference, still with the ELT, this is not an easy thing, yeah? So there have been many simulations that have been run in the consortium, and we have so far a preliminary golden sample of exoplanets that might be most amenable to detections of their reflected spectra with the setup that we have for Andes here. So what you're seeing here is basically the Y and H bands. Remember, if you want to do AO assisted, we can't get the visible and the blue range. We're going to the redder range for this. And you can actually see here that we are talking about significantly longer time investments that we actually have to make. So just a little bit of chit-chat from the science team. We actually had long discussions about how much time do we want to invest for which number of exoplanets to target with this, right? Because we are talking about a relatively modest size of exoplanets that we can do, for example, in the guaranteed time for this instrument. You see them here, yeah, that we can target here. Proxima Cent-B is sitting here. This is one of the cases where the number of nights is not so large, but you can see here we're going basically up to 15 nights, or days as it says here in this plot, to actually get these spectra detected. Now, a challenge that we will have in any case, and this is also something you have heard a few times at this conference, is the stellar contamination is not something that is easy. We do need methodological progress over the next decade to figure out how our best processes should look like to deal with the data. So with the temperate planets, obviously we have slower orbital acceleration that we need to deal with. And therefore we need to figure out what the star is doing. We need to characterize the star much, much better and understand what's happening there. One thing I would like to really emphasize here, if you care about stellar activity, so this is from my colleagues in the solar group, if you want to see which lines are actually most sensitive to activity changes, what you're seeing here is basically a small part of the sun where a small flare happened, and you see here that the calcium-2 H and K lines in the near UV react much more strongly to activity changes than anything else that we typically think of as chromospherically active lines that are accessible in this wavelength range. So this is really important stuff. Now, I want to quickly talk about the goals, so basically the extensions of Andes to the K-band and the U-band. If we are able to add the K-band to Andes, then there's really interesting science we can do, and we will hope to be able to do so. You all know that especially CO detections and spectra led to many interesting discoveries over the past years. Many of them are mentioned here. And Andes with the K-band could become such a CO machine and enable lots of interesting things, wind patterns, spatial mapping of exoplanets, and a push towards the smaller planets for this. In the U-band, which is the other goal at sort of the other end of the wavelength range, I think this is really important to enable us to reach our main science goal, because we have this most sensitive activity doublet of lines basically sitting there that we can work with, that we can characterize the star with, and that is sitting in the U-band. We actually need that to see that. There's also interesting science cases, for example, aiming for Rayleigh scattering. You could also think about ozone absorption. That's not super easy because it's broader absorption bands. Could be very interesting. And also probing for atmospheres of lava worlds. So we have lots of exciting things coming up with Andes. We do need methodological progress. And now I'm going to completely switch gears and show you a little bit of what I've been working on this year and what I'm having fun with. So what I am doing at the moment with some people in my group is we're looking a lot at helium observability in exoplanet atmospheres. You've heard a few talks about that this week already. And you also probably know, if you care about this, that the helium absorption here in scale heights plotted, right, that depends on the incident X-ray and UV flux that the planet receives. This is this whole business of actually getting the helium into the metastable state so that you can then see it in your transmission spectra. And now, in principle, that's all fine, right? So this is kind of what you would expect in such a plot, right? And the question is, why are there actually so many non-detections of helium in those atmospheres? This is kind of weird that we have this blob of things. And it's not because they don't have atmospheres, because like there's old friends like WASP-121b or HT189. Those things do have hydrogen-helium atmospheres. And why are they not where we expect them to be? And I think a big part of the answer lies actually in the stellar spectra. Because this thing here, what we plot on the x-axis, is typically a broadband estimate that we base on some other part of the spectrum, because this range we cannot typically observe. There's the ISM in the way. We are practically blind after 10, 15 parsecs. Yeah? So if you look at a few of those spectra in exactly this narrow range that drives the metastable the helium into the metastable state, you actually find that this spectrum here, this is what I'm showing here, yeah, is dominated by just basically a handful of emission lines. And if you have a K-star, for example, yeah, you see a lot of emission lines there. If you go for an active M dwarf, where you would think, okay, much more XUV emission overall, that part of the spectrum is really poor in emission lines. So I think characterizing this really narrow range of the extreme UV will really unlock why we see such weird things here and why some of our planets that we should have seen in helium actually lead to non-detections. This is challenging stuff. You have to do interesting differential emission measure analysis from high-resolution X-ray spectra. This is stuff I really, really love as a stellar physicist, and I think it's going to be a lot of fun, and I hope we can make a lot of progress from the stellar side to clear up what we should actually expect to see in our planets in the helium line. And that's everything I wanted to tell you. Thank you.
Our next and final speaker of the day will be Chad Bender, who will talk to us about LFAST.
All right. Oh, wow, that line is really close. Okay. I'm really pleased to be here today to tell you about a little project that we're working on at the University of Arizona Stewart Observatory. This is a medium-sized telescope and instrument team that we have put together right now, but with a lot of experience building telescopes and instruments over many decades. And I'm not going to talk much about science, but I don't really need to, because everyone else in the conference has really motivated this facility extremely well, including Katja. I think that was a nice setup for exoplanet science at the ELT level. So the Large Fiber Array Spectroscopic Telescope, also called LFAST, and we have a couple of science team members here in the room, Emily Gilbert and Megan Mansfield. So let's just get started. Ground-based astronomy has a big problem. We want bigger and bigger things, and they cost more and more money. And this is not sustainable. So there's this very well-known cost to aperture curve that is a power law to the 2.5. And no matter how you hide the labor that goes into your telescope, and the US and Europe do it differently, an ELT, whether it's the GMT, the TMT, or the ELT, are $2 to $3 billion facilities. And if you say, I can't do my science, which in this particular case is spectra of a Earth mass habitable zone exoplanet around a sun-like star with one of these telescopes, and you say, I need to build a bigger diameter telescope, you have a serious problem, because now it's $10 or $50 billion, and that's just not going to work. We build a lot of big telescopes in Arizona. There's another problem here. Those 8-meter mirrors that pop out of the Mirror Lab don't really pop out of the Mirror Lab. They take 4 years to make each one. The GMT, by the time it goes on sky, will be a 30-year project at $2 billion. LFAST is trying to get the collecting area of the ELT, or 6 ELTs, for 10 to 20 times lower cost and at dramatically faster speed. So this is the only science slide, and it's got a lot of words on it, so I apologize. And it's not all exoplanet science. The phase telescopes are great. I love phase telescopes. They can do amazing things. We should be using them for things that require high angular resolution. If you're using your giant telescope as just a light bucket, and you don't have a good reason to use it like that, you should think very carefully about whether that's the best use of the telescope time, or maybe, and now I'm sinning here a little bit, you give it all to the AO guys. But there is a huge demand for on-demand spectroscopy at medium to high resolution. It's not just us. LSST Rubin is going to start producing a huge number of targets that need rapid follow-up and long-term continuous follow-up at these resolutions. And we don't have a plan right now for what to do with that. There's also all sorts of non-time-dependent high-resolution things that can be done when you can collect a vast number of photons out in the intergalactic medium, evolution of the universe, cosmological constants, all sorts of things. I'm not an expert on any of those, but if you are interested in them, reach out to Dennis Zaritsky, who's our project scientist. We are all familiar in this room with detecting molecules in exoplanets. This is an old example, and I give this talk a lot, and it's stuck in there, and I didn't update it for you folks who are more sophisticated than the normal audience that sees this. But we all know that JWST has been detecting molecules in the atmospheres of planets. This was one of the early release results from right after launch. It's a 300 part per million transit depth of water. It's a 6-hour observation. It's a hot planet in a short orbital period, and they found it, and that's great. But if you do the very, very simple Astro 101 signal-to-noise photon scaling math to a Earth, it does not work. Ever. So probably right now we don't have any of those targets, and Emily has showed a good one this morning that's around an M dwarf TOI-1518b. But the problem here is the spectral features are 40 times shorter or shallower than WASP-96. It has many fewer transits, so you cannot observe it as frequently. To do that with JWST, you would need 3,000 transits, which will not work. It is a problem. There is no magic here. This is root-in photons. And we saw this also from Arthur Wiegand on Monday. Half a photon per day. We need more aperture. Kevin Hardegree-Ullman put out a very nice paper about a year ago modeling what can all of the ELTs do if you're going after biomarkers like oxygen. Hypothetical Earth-like sample, because they don't exist yet, but he created some, distributed them in the 20 parsec regime, and applied window functions for transit duration, orbital period. What happens if the transit happens and your telescope is on the wrong side of the planet, so you miss it that year and you gotta wait a whole nother year, etc. And O2 is a very faint signal. It's not a good, easy to detect signal. The answer is that if the GMT, the TMT, and the ELT all collaborate together, and on one target, it's like a 30-year project, something like that. Not good. If we want to go after true biomarkers, we need more aperture. We also probably need to characterize those planets, as we've been hearing about today, out in the infrared for CO2, CO, ammonia, et cetera, to make sure that they're worth investing a decade of time going after a biomarker, because if it's not a terrestrial-like atmosphere, then we should just stop with that target. Unless we're interested in doing atmospheric physics, which is a whole different thing, but less sellable to the public. So, LFAST is a scalable array of small telescopes. This is not a new idea. Roger Angel, who's my co-PI on this, had this idea in 1977. You build small telescopes, you combine them with optical fiber back to a common spectrograph. Optical fiber in 1977 was new, and that's what triggered the idea. It's been 50 years. We've done a lot of things in the meantime, built a lot of big telescopes, come full circle on this. So we are building telescopes based around a 76 centimeter diameter spherical mirror, f3.5, pretty slow. And we take 20 of those and we put them on a common mount in a fairly simple frame, steel frame, and that gives you the aperture of the WIN telescope, a 3.5 meter telescope. 10 of those is Keck, 130 of those is the ELT. The other difference here is that we're building the same system over and over again. We're not doing it like astronomers, we're doing it like industry who knows how to make things not cost power law to the 2.5. Once you engineer this, you have a production line and they roll off like iPhones, hopefully. Now, that's a little flippant, but that's the goal. You can pack them fairly tightly. The whole array, the ELT, it's not that much space. It's about the size of a standard football stadium. It's about 100 meters on a side. So it's not a small space, but it's not an enormous space. Here's the optical diagram. These are simple. Spherical primaries, 4-element refractive prime focus corrector. The fourth element of that is movable, and it gives you an ADC correction and a high-speed tip-tilt correction for bright targets as well, which for a small mirror is important because you can get back most of your Zernike losses, like a 30% throughput improvement, by doing tip-tilt correction. We have a 8 arc-minute guider that around each fiber is potted in a metal puck, and so we can guide. The wavelength regime is limited by the ADC performance, which is optimized for 400 to 1.8. But that's a very interesting range for this room. So I have a lot of slides on hardware, and I combine them all into one. But if you have a particular interest in the subsystem, ask me, and we can talk afterwards, and I can show you pictures. We have mirrors that we make in-house that are being tested right now. The prime focus corrector optics have been contracted out to Edmund Optics and are arriving imminently. Some have already arrived. We'll have 25 sets in-house by the end of the summer. And we are learning how to do that high-speed tip-tilt correction in the lab and hope to deploy it on Sky later this fall. We're also doing quite a bit of fiber development with very small core fibers. We're not single mode, unfortunately. We're 18 micron fiber, which is the small telescope aperture matched to a 1 arc second sight. That's a very annoying place to be, but that's where we have to live, and we're learning how to deal with that. The guider, I think, is really important for this room, so I left this slide on because we want every photon that we can get. We need to collect the photons rapidly during the transit. This is not a cosmology project where you can just stare longer. If you miss them in the hour that you've got, you gotta wait. And so we expect that we will be able to activate the high-speed correction down to R of 11, and we're looking at how do we improve that bandpass and push it a little further so that we make sure that our highest priority exoplanet targets are accessible to this telescope. We're limited because the primaries themselves are fairly small. So, this thing is also fairly real. This is not a concept talk. We're moving very quickly. This frame that you see here arrived at our integration facility 3 weeks ago while I was in Japan at SPIE, and it was craned together with a very big crane. It is approximately 4 horses tall in this stowed position. When it is in the upright position, it's another horse and a half. It's a big structure. This holds 20 telescopes. It's about 5 meters on a side. Eric, our engineer who's standing there, is not a small person. We anticipate integrating telescopes into this, first testing it on sky to make sure it's not going to shake itself apart, that we can control wind shake and things like that over the next few months. If you've been to Tucson right now, you know that this is not the time to test a telescope. It's very, very wet. But coming out in the fall, we'll be testing this on sky, in fact, right where you see it right now, and then we'll be populating it with mirrors for testing at Tucson level later in the fall, and then up to a mountain site near us that I can't name publicly yet shortly thereafter. The spectrograph, I haven't talked about at all. We're still in the concept design phase for the spectrograph. The Aton do is horrific, and we have the same problem as Andes except worse. But our goal is to build one or a few spectrographs to meet the science case, and we're already sliced a lot, so it's a matter of putting the slices back together, which is a different, flipping the problem around from how we normally tackle this. But we're intending to build an optical wide bandpass spectrograph up to 150,000 resolution and a visible spectrograph at a more moderate ice shell type resolution or something like that, 80,000. The extragalactic science cases need lower resolution. When you tell them what can you do with 100,000, they kind of look at you mostly and don't know. But if you have input on this, we welcome it. We're still doing the trade studies on this. This project is coming together a little differently than your normal astronomy project where we spend 10 years sitting around and talking about everything and setting requirements. We're building things before we have the requirements set, and it's all kind of hopefully going to ooze out at the end in something that's, you know, functional. We built a prototype. This has been on sky. This is one mirror. It's not a very good mirror. It has a lot of astigmatism. You wouldn't want to do science with it, but it does in fact produce fairly decent images at Tucson level where the seeing is 4 arc seconds. We've been on sky quite a bit doing shakeouts of drive systems and mirror control systems and things like that. And so we have some pictures. We did manage on one night to split a 5 arc second binary, which doesn't sound that impressive, but the seeing was like 3 arc seconds and the mirror has a lot of astigmatism. So we were not super upset about that. And so I'll stop with this slide with a project schedule on it, which is quite a bit more rapid than your typical telescope project, at least at this scale. So we're in the 3rd year of a 3-year design phase study, and so by the end of that, we intend to have built, we should have built a 3-meter telescope that is on sky and functional. And then we will start what we think is probably another 3-year timeline to build the 10-meter class array, and once that is functional, build it out, continue building it out at a much more rapid production rate to an ELT-sized array, and once you've got that production line running, you might as well just keep the mirrors chugging off the assembly line, and then you build half a dozen of these and you spread them globally, and now you've solved the problem of my transit happened on the other side of the planet, because I have a spectrograph and a telescope on the other side of the planet. The supernova people are also very happy because they can follow things continuously. So, some thoughts at the end. as I said, it's important to get involved early in these projects. By PDR phase, it's too late. The requirements are already set. So if you have requirements that you think are important, that we should be accounting for, or you want to weigh in, come find me. If you don't find me today, send me an email. Early career folks, there's been a lot of people advertising for jobs and a lot of people looking for jobs. You're going to be the users of this, and you should think about what capabilities you want. Instrument builders are generally pretty friendly people. And it's also worth pointing out that instrument projects tend to be long, and they tend to be better funded than many science projects that are based on individual grants. So if you're looking for a different way in the field, or you're interested in instrumentation, it's not the traditional, probably, you know, I get a postdoc and I write a bunch of papers, and then I get the assistant professor job and blah, blah, blah. But there are other ways in, and instrumentation is a very interesting one, and we need more people who are interested in it. So if you're interested, let's chat. Thank you.